Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. A lone figure drifts at the window of an orbital outpost. Below, Earth glows blue and cloud, swirled, a fragile orb suspended in darkness. The person's face is gentle with awe, but their eyes carry a question. Could we live here? Not just visit for a while, but live, truly make a life in the cosmos. The silence of space answers with its own question. The Earth slowly turns beneath them, and they wonder, what if this station, this void, became not just a workplace, but a home? What if one day they do not return, because this is home now? The hum of life support is the only sound. Heartbeats and hopes float in microgravity. As Earthrise paints their view, they press a hand to the glass, imagining a future where the bright cradle of Earth is behind us, and ahead is a new frontier on the assessment of effective stimuli and stage alteration in mood. Throughout history, we have sought to learn about the world around us, find new resources, and improve our existence. As one space agency now puts it, the dream of space is the dream of freedom from limits, a dream that carries the hope of discovery and perhaps a sense of destiny. We feel it when we stand in a dark field and see the Milky Way arch overhead, the quiet pull of something beyond. It's the same impulse that led nomads over distant hills and sailors across uncharted seas. Since the dawn of humanity, we have explored to understand, to survive, and to see what lies beyond. Now the hills are skyward, the next ocean is the vacuum of space. The longing for the stars is timeless, woven into art, religion, science, into our very language when we speak of aspirations as reaching for the stars. This dream has always been about more than survival. It's about wonder. The poet in an astronaut's heart feels the same awe as the child watching a shooting star. We carry our dreams upward, generation by generation. And as we finally broke the bonds of gravity in the 20th century, that ancient dream only blazed brighter. We realized the stars are not just distant lights, they could be destinations. Humanity's longing became a plan. The first steps, history of human spaceflight, and the temporary nature of our early efforts. When at last we found a way to ride fire into the sky, the world watched in collective breathlessness. Those first steps into space were halting and brief, glorious yet temporary. The early astronauts and cosmonauts launched into orbit were like divers dipping toes into a vast ocean, always tethered to the shore of Earth. In the 1960s, human beings orbited Earth for minutes to hours, looked out the small windows at our blue planet, and then returned home the same day. Soon after, footprints were pressed into the grey dust of the moon, a moment monumental and yet fleeting. Those pioneers spent mere hours or days on lunar soil before coming back to Earth's embrace. Each mission planted a flag, but also left the moon empty of humans once more. As one observer noted, the earliest journeys beyond Earth were the work of a few 100,000 people over a decade, culminating in brief triumphs. We proved it was possible to leave home, but we did not stay. Throughout the 1970s and 80s, we established small outposts in orbit, Skylab, Salyut, Mir, places where a handful of people lived for weeks or months at a time. Yet those stations were always considered temporary homes. The crew members knew their address in space had an end date, a return ticket. Indeed, the longest continuous stay any human managed in those years was about 14 months, an unprecedented endurance test by one cosmonaut. But even he eventually came back down to Earth. No person has yet lived and died in space. All have so far come home. Our species has not truly emigrated, only camped abroad. Even today, on the International Space Station, where there has been a continuous human presence for over 2 decades, astronauts rotate in and out like research staff at a remote outpost. Each individual stays roughly 6 months, maybe a year, and then returns to gravity and open air. The ISS itself has shown that we can live continuously beyond Earth as a species, but it is a relay of temporary crews, not a permanent settlement for any one person. They orbit 240 miles above Earth, which feels both incredibly far and yet cosmically close. The crew still sees Earth filling their window and knows a ride home is just hours away. In these first steps, the pattern was clear. We always came back. The early spacefarers experienced wondrous things. The first Earthrise viewed by Apollo 8, the fragile horizon of our atmosphere seen from orbit. And they also felt in their bones how special Earth is. After each mission, boots returned to touch familiar ground, and hearts carried new perspective. Space was transformative, but it was not yet home. Perhaps it had to be that way. We were testing ourselves, testing technologies, taking baby steps out of the cradle. Early spaceflight was driven by competition and curiosity, not by a desire to forsake Earth permanently, and so our habits remained temporary. We packed enough air, water, and food for a journey, never planning to grow old out there. The moon saw astronauts' boot prints and laughter, but no towns or children's playgrounds. Now, however, the conversation has shifted. The question arises in planning meetings and late-night reveries. What if our future missions do not have to end back on Earth? What if one day, the return ticket is optional? We stand on the shoulders of those who PR are all being studied to preserve bone and muscle, acknowledging that we cannot live normally long-term without confronting this challenge. Other changes are more subtle but palpable. Fluids in the body, no longer pulled down by gravity, shift upward. Faces become puffy, legs thin out. Astronauts joke about the Charlie Brown appearance of big round heads and skinny limbs. More seriously, that fluid shift puts pressure on the skull and eyes. Many spacefarers have reported blurred vision after months aloft. In some, the shape of the eyeball actually changes, a condition now termed spaceflight-associated neuro-ocular syndrome. There is no up or down. After a few days, most adapt and can move around gracefully, but when they return to Earth, the process reverses. Suddenly they feel extremely heavy, dizzy, and weak. It's common for astronauts to faint upon standing after landing, due to O often reactivate in astronauts, indicating immunity isn't quite right. The landmark one-year mission study of a twin astronaut found shifts in things like chromosome telomere lengths and gene activity during the long stay in orbit. Most of those changes returned to normal after some time back on Earth, a reassuring sign of resilience. Yet it demonstrated that the body truly is rewriting its operations to cope with space. Some changes were positively assuring, suggesting adaptation, but others raised questions about subtle long-term effects. Radiation plays a role as well. High-energy cosmic rays permeate spacecraft and can quietly damage DNA. And some astronauts indeed have developed painful kidney stones after flight. Back pain is frequently reported in orbit as the spine decompresses and lengthens. Sleep can be disrupted too, without a normal day-night cycle. And with the subtle physiological changes, many astronauts struggle with insomnia or fitful rest. Despite all this, humans can survive and function in space reasonably well for a time. We've learned to mitigate many issues: rigorous exercise fights, muscle and bone loss. Special lower body suction devices can pull fluids downward to relieve head pressure, and medications or dietary tweaks help with other imbalances. But the takeaway is humbling. Microgravity touches every system of the body, reminding us that we are creatures of Earth trying to live away from it. If we truly wish to make space our home, we must redesign our homes or ourselves to account for this. Perhaps we create artificial gravity in our habitats to let our bones and muscles work. Perhaps we develop new medical therapies to prevent bone loss or enhance muscle growth in low gravity. Already, scientists study drugs like bisphosphonates to see if they help retain astronaut bone mass. We even consider genetic or technological augmentation in the far future. Could people engineered for space have stronger bones or radiation-resistant cells? For now, each person who slips free of gravity understands viscerally how much our bodies belong on the ground. One astronaut, drifting in the ISS, remarked on the strange freedom. "You feel like a ghost with no weight," he said, "but your body is working hard to adjust to that ghostly state." It is an ongoing adaptation, a testament to human plasticity, and also a warning. Our bodies can adapt to microgravity to an extent, but not indefinitely, and not without support. Living in space long-term will mean continuously tricking or aiding the body, either through habitat design that simulates gravity or medical interventions that counteract the deleterious changes. We carry Earth with us in our flesh and bones. To live among the stars, we'll have to become shepherds of our own biology in a way never before required. The mind in space, isolation, psychology, and the need for connection. In the silent confines of a space habitat, it's not only the body that faces trials, the mind is tested in profound ways. Imagine months encased in a steel shell, with the infinite void outside and only a handful of other souls for company. No fresh breeze, no changing scenery beyond what the small porthole shows. This is isolation on a level few humans have experienced, and it can play tricks on the psyche. We are social creatures by nature, tied to the rhythms of Earth, the day-night cycle, the bustle of life, the comfort of Earth's ground under our feet. In space, much of that familiar context is stripped away. What does that do to a person's mental landscape? From studies in polar stations, submarine patrols, and simulated Mars habitats, we've learned that long-term isolation and confinement can lead to a cascade of psychological challenges. Mood and motivation can wax and wane. Small annoyances with crewmates, a loud habit, an inconsiderate remark, can fester in the pressure cooker environment where there's no easy escape from each other. Even those carefully selected for resilience and compatibility feel the strain. Astronaut crews are indeed chosen and trained with team dynamics in mind. They undergo team-building exercises and psychological evaluations to ensure they can handle living and working together for 6 or 12 months. Yet conflicts and tension are not unheard of, especially in longer missions. People can become withdrawn or irritable. In the famous year, long Mars simulation studies on Earth, journals revealed how the crew went through periods of monotony, interpersonal friction, and homesickness. One striking phenomenon observed in long-duration missions is the so-called third quarter effect. When a mission is about 3 quarters completed, far enough in that the novelty has long worn off, but still not close enough to feel the excitement of near completion. Morale often dips sharply. Studies of 520-day isolation experiments noted stage-like patterns, an initial upbeat phase, a slump in the middle, then sometimes A and BH and play in their off time, finding solace in creativity. NASA also discovered the benefits of a simple garden, tending plants in space, watching leaves unfurl and flowers bloom, has a calming, morale-boosting effect. Several astronauts have spoken about the joy of smelling fresh leaves or touching soil, a sensory reminder of Earth that soothes feelings of alienation. One crew even celebrated when their small space-grown lettuce was ready to eat. That salad, though humble, represented life and normalcy in an alien place. Another powerful tool is journaling. Astronauts are encouraged to keep private journals of their thoughts and feelings, which they can choose to share later with psychologists to help understand behavioral issues. Writing offers an outlet to vent frustrations safely. Many crew members report that writing down worries or reflections helps keep them emotionally stable. It's like talking to a patient confidant who is always available, the blank page. Virtual reality and communication tech are also being explored to ease isolation. Imagine donning VR goggles, and suddenly you're virtually sitting in your old living room with your family for a chat, or walking through a green forest path that feels almost real. Researchers are testing VR experiences as therapeutic escapes for crews on long missions. Early studies suggest this can indeed improve mood, a brief psychological vacation to earthly settings to relieve the confinement. Still, challenges remain that technology can't fully fix. Cultural differences can emerge in international crews. Misunderstandings might arise from different norms or language nuances. Crews must practice exceptional communication skills and empathy, developing a sort of family bond. When problems occur, they have only each other to rely on, a double-edged sword, because strong cohesion is protective. But if relationships sour, there's nowhere else to turn. Mission Control on Earth provides psychological support too, scheduling regular private conferences where astronauts can speak with a psychologist or counselor, and offering advice for team tension if needed. They also orchestrate morale boosts, occasionally surprising the crew with care packages, or coordinating simultaneous meals with family via video, link, etc., to keep spirits up. In deep space, beyond Earth's immediate vicinity, an additional psychological specter might arise: the Earth out of view phenomenon. Thus far, even on the Moon, astronauts could always see our bright planet hanging in the sky. But on a mission to Mars or further, there will come a point where Earth shrinks to a mere star-like point. Psychologists speculate that truly leaving Earth behind in that visual sense could induce a profound feeling of severance, an uncoupling from Earth that might cause anxiety or depression in some. One might feel unmoored, like an exile cut off from the collective human hearth. In literature and simulations, people have imagined that moment, a crew member staring out a porthole and no longer being able to identify which tiny dot is Earth. It's a moment of existential loneliness. Will future spacefarers find inner resilience and purpose to push through that? Or will some succumb to a kind of spacefarer's melancholia? Knowing this risk, mission planners are thinking ahead. How to prepare astronauts for that psychological shift, perhaps through training or through group discussions addressing the meaning of their journey. Interestingly, while isolation can harm, it can also engender unexpected strength and insight. Many astronauts report that in the struggle with solitude and confinement, they discovered new wells of creativity and spirituality. Some talk about the intense camaraderie that forms, a band of brothers, sisters feeling, where their small crew feels like an entire world and family unto itself. They celebrate each other's birthdays with genuine warmth and invent rituals aboard their spacecraft to create a sense of community. And upon returning, quite a few express a deepened appreciation for simple human contact, nature, and daily life. In a sense, the psychological challenges of space might make those who endure them more reflective, more grateful, and sometimes more connected to humanity than ever. In the end, the mind in space craves what it has always craved: connection, purpose, and a touch of the familiar. As we plan to live in space, equal attention must be given to building environments and routines that feed the human soul, not just keep the body alive. That means spaces that allow privacy when needed, means of communication that keep loved ones close in heart, and activities that give astronauts not just work, but life in space: music, art, humor, even intimacy and friendship. The stark void may surround them, but within their habitat, we must weave threads of home. Our psychology demands nothing less, because though we leave Earth, we carry all the emotional needs of Homo sapiens with us on the journey. The void of space is a grand frontier, but the void in one's heart must be kept filled with the light of human connection. That is as critical to survival as air and water. Artificial gravity, engineering gravity through rotation. Every evening on the space station, astronauts strap themselves to a treadmill and run, their bodies yearning subconsciously for the feeling of weight on their bones. As their feet pound the moving belt, their minds can almost trick them into feeling normal, almost, but not quite. True gravity remains absent. Yet, what if we could bring gravity with us into space? This question has been asked for as long as humans have imagined living off Earth. The most promising answer is both elegant and old in concept. Spin the spaceship. Artificial gravity by rotation relies on the simple physical principle that a rotating ring or cylinder will fling objects inside it outward, simulating the push of gravity. In a spinning habitat, down would be toward the outer hull, as centrifugal force presses inhabitants to the walls. Generations of science fiction films have depicted such stations, from slowly turning wheel-shaped stations to giant spinning cylinders with landscapes on their inner surfaces. In reality, we have not yet built a full-scale rotating habitat for people, but engineers have studied it extensively, and we have little doubt it can work. The challenge is how to do it practically in space in a rotating environment. You need a certain combination of spin rate and radius. If the radius is large, say a huge wheel a kilometer across, you could spin it gently, maybe only a rotation every minute or two, and the outer rim would provide near 1 G without making people dizzy. However, building something so vast in space is far beyond our current capabilities. If the radius is smaller, a more modest station tens of meters across, you'd have to spin it much faster to get 1 G, perhaps several rotations per minute. But humans are sensitive to rapid rotation. The inner ear can get upset, leading to motion sickness. Research from spinning room experiments on Earth indicates that most people can adapt to rotation rates up to perhaps 4 rotations per minute after some days, though at higher rates like 10 RPM, nearly everyone initially experiences strong disorientation. Fortunately, adaptation does occur. Test subjects who spent days in a rotating habitat on Earth found that after a while they could move normally without sickness at moderate spin speeds. But to be safe and comfortable, designers often aim for a spin rate of 4 RPM or less. At 4 RPM, to achieve 1 G, you'd need a radius on the order of 56 meters or so, a structure over 100 meters across in diameter. That's still huge, but potentially within the realm of future construction in orbit. Larger radii allow slower spin. For instance, a classic design from NASA in the 1970s, the Stanford Torus scientists worry that even Mars's gravity might be insufficient to fully prevent bone and muscle loss, or to allow normal pregnant. The docking of ships to a spinning station is non-trivial. Perhaps you'd have to match rotation, or momentarily halt rotation for arrivals. There's also the matter of scale. To spin comfortably, bigger is better, but bigger means heavier and costlier to launch and assemble. We may need to master in-space construction, using robots or 3D printing, to build such megastructures piece by piece in orbit. Despite these hurdles, small, the allure of artificial gravity is strong because it directly tackles the root of so many problems. With gravity, astronauts would walk rather than float, giving their bones constant exercise. Fluids would settle normally, no more puffy faces and stagnant headward fluid. Showers and toilets would function more conventionally with weight to make water flow downward. Sleep might improve as the body feels the normal pull that it evolved to expect in rest. Eating and digestion would be simpler without food floating about. Essentially, it would allow a truly Earth-like living experience even in space. However, artificial gravity through rotation isn't a perfect recreation of Earth gravity. One quirk is the gravity gradient in a small spinning habitat. Your head, closer to the center, experiences slightly less centrifugal force than your feet. In a small radius, you might feel perceptibly lighter at your head than feet, an odd sensation. Also, any movement not purely tangential can cause Coriolis effects. For instance, in a spinning environment, if you drop an object, it won't fall straight down to the floor, but appear to curve a bit because of the rotation, something one would adjust to. If you turned your head quickly, you might feel a strange twisting in your inner ear, which can cause dizziness. But as experiments show, people can adapt to these as long as the rotation isn't too fast. After a day or two, Many can function in a rotating room, almost as normally as in a static one. One can imagine the first rotating space city, a great wheel that spins in the void, sunlight streaming through its windows. Inside, children might play in a park with green grass, under a blue sky, created by centrifugal force, holding air and allowing clouds of water mist. Those children might not even realize at first that their world is artificial, except maybe when they notice that birds flying in the direction of rotation have to flap a little differently. The floor is curved, giving the S of a bowl. The horizon curves up. Yet they feel weight and can run and jump. For them, artificial gravity isn't artificial at all. It's just gravity, a constant companion, allowing life to flourish in space, as it does on Earth. In the nearer term, we might start smaller. Perhaps a Mars ship with a tether and a cargo counterweight, rotating slowly to give the crew maybe Mars level gravity during cruise. This could dramatically reduce the deconditioning they experience en route. They would arrive on Mars much readier to walk and work. A free-flying station in the 2030s or 2040s, built by commercial companies, might incorporate a rotating habitat module. Some have pitched designs like a dumbbell station, rotating to provide even partial gravity as a butt easier to shield against with proper shelter. Then there are the galactic cosmic rays, which are the nuclei of atoms accelerated by distant star explosions. These are extremely penetrating. They slice through spacecraft walls and human tissue alike, breaking DNA strands and knocking electrons from molecules. Over months and years, this cosmic rain can significantly increase one's risk of cancer and cause degenerative effects like cataracts or heart disease. There's even evidence from animal studies that cosmic rays might harm the brain over time, potentially impairing cognitive function or inducing neurological issues. Mice exposed to heavy ion radiation, akin to GCRs, showed memory and learning problems and signs of brain inflammation long after exposure. So when we speak of settling space, this is a silent threat we must address. A colony on Mars or a ship en route to Jupiter will be bathed in more radiation than any place on Earth. How much more? On the International Space Station, astronauts receive on the order of dozens of times the radiation per day that we get at sea level. A 6-month ISS stint might expose someone to around 50,100 times a chest X-rays worth of radiation dose. On a voyage to Mars, without Earth's magnetic field, that could roughly double or more. And in deep space beyond Mars, GCR flux is fully unleashed. Consider an extreme scenario. In August 1972, between the Apollo 16 and 17 moon missions, a massive solar flare erupted and shot out a storm of high-energy particles. Had astronauts been on the moon during that event without a thick shelter, they could have received a potentially lethal dose within hours. It was a lucky timing that no crewed mission was there. This event was a wake-up call. Any long-term habitat must provide a storm shelter where crew can hunker down during solar events, surrounded by extra shielding to absorb the sudden spike of radiation. Typically, water or special plastics are good for such shelters, since hydrogen, rich materials block solar protons well. On a Mars cruise ship, for instance, they might line a small closet or module with supplies that double as radiation absorbers, and crew would crowd in there for a few hours during a solar flare warning. For the chronic background of cosmic rays, more continuous shielding is needed. Shielding design becomes a crucial aspect of space architecture. Different materials have different shielding properties. Metals like aluminum stop some radiation, but when struck by cosmic rays, can produce secondary showers of particles that are themselves harmful. Research shows that hydrogen-rich materials are more effective because they produce fewer secondaries. This is why plastic materials such as polyethylene are excellent shields. They're full of hydrogen. Polyethylene is about 50% better than aluminum of the same mass at shielding solar flare radiation, and 15% better for cosmic rays. There's talk of incorporating plastic layers in spacecraft walls or even using water itself as a shield. The walls of future habitats might include tanks of water or fuel that serve double duty, useful for life support, and also placed strategically to encircle crew quarters with a protective envelope. On Mars or the Moon, one obvious strategy is to use the local dirt. Martian colonists could shovel Martian soil on top of their habitats or live in structures. Just a meter or two of soil can cut radiation dramatically. The moon-based designs often include habitats covered by several meters of lunar regolith, blocking not only radiation but also insulating against micrometeoroid strikes and extreme temperatures. Innovative ideas are abound. Some propose inflating big plastic modules and filling their walls with water or even liquid hydrogen fuel. Great for shielding, but complex to implement. Others look at active shielding, generating magnetic or electric fields around a ship to deflect charged particles, essentially creating a mini magnetosphere. In theory, this could work, but the field strengths required are huge, demanding superconductors and power, and there's weight and safety issues. A study showed you'd need something like a 10+ Tesla superconducting magnet ring around a ship to significantly cut GCR exposure. That's technology we don't yet have for large scale. Passive shielding remains the go-to solution for now. So as we plan habitats, we deliberately design in thick walls, especially around sleeping quarters where people spend lots of time. For example, spacecraft may put storage modules around crew quarters to act as buffers. There are trade-offs. You can't shield everything heavily or the mass becomes prohibitive. Thus, mission planners set exposure limits. Under those limits, a Mars mission is borderline. Some scientists say current shielding plus travel time would lead many astronauts to reach or exceed safe limits, which is partly why reducing travel time and adding shielding is key. On the surface of another world, like Mars, radiation is still a concern. Mars has a thin atmosphere that offers only modest protection. It also lacks a global magnetic field. So settlers there would get a chronic dose roughly several times higher than on ISS. Over a year, that could be significant. They will likely live in habitats that might be built into Martian hillsides or covered with sandbags of Martian soil for safety. The romantic notion of a glass-domed city on Mars conflicts with radiation reality, unless that glass is actually a multi-layer composite with radiation absorbing layers. Even then, during a solar storm, colonists might have to retreat to deeper shelters. Some plans foresee underground habitats in lava tubes, where meters of rock overhead naturally block cosmic rays completely, a very attractive refuge, though cave living has its own challenges. Radiation does more than increase cancer risk. It can weaken the body in subtle ways. For example, astronauts have reported changes in their blood counts and hints of impacts on their immune system after long flights. Cataracts have appeared earlier in some astronauts' lives, likely from space radiation exposure. There's concern about fertility. Cosmic rays could damage sperm or egg cells, or harm a developing fetus. If we imagine multi-generational space communities, we must solve radiation protection for the unborn and children, who are especially sensitive to radiation's effects on growth and DNA. That might mean particularly heavily shielded nurseries and schools in any space settlement, may be literally encased in water tanks or regolith for extra safety. Hope lies in clever engineering. A combination of passive and active techniques could bring radiation down to levels comparable to what high-altitude pilots or miners on Earth face, still above normal background, but perhaps manageable. The Artemis Accords, an international guideline for lunar exploration, explicitly state that resource extraction for shielding is allowed. Countries and companies know that without addressing radiation, sustainable presence is impossible. So, lunar base concepts often include robot-built berms of soil around landing pads and habitats. The first habitats on Mars might be 3D, printed from the local dirt, forming thick walls even if the inside is pressurized inflatable sections. In orbit, A possible intermediate solution is a storm shelter module on stations, as mentioned. Basically a small, heavily shielded safe room. Already on ISS, there is procedure during solar flares. Crew go to the most shielded parts of the station and avoid spacewalks. Future deep spaceships will definitely have a designated spot with extra shielding for such events. But day to day, the whole living space needs reasonable shielding too to avoid cumulative harm. Beyond technology, we may also rely on medicine. Pharmaceuticals like radioprotective drugs are being researched, pills that could bolster cells' resistance to radiation or scavenge free radicals caused by it. On Earth, certain drugs are given to people undergoing radiation therapy for cancer to protect normal tissues. Perhaps spacefarers will take a daily rad shield pill. Even dietary antioxidants are suggested to help mitigate radiation damage to some degree, so diets might be adjusted. However, these are supplementary at best. Nothing beats physical shielding to stop the particles from hitting you in the first place. In summary, radiation is one of the most formidable barriers between us and comfortable life in space. But it's a physics and engineering problem we can solve. Thick materials, smart placement of resources, and possibly active deflection systems will together form an umbrella over future space habitats. In the black of space, you can imagine seeing a faint blue-green glow around a large spaceship, maybe an artificial magnetosphere at work, or shielding panels glittering. Inside, children play without fear, not realizing that beyond those walls, lethal rays are being tamed. On the moon, colonists might live in habitats that to an outside observer look like mounds of dirt. Humble burrows that hide vibrant human homes safe from the sun's tantrums. When we finally set sail to the stars, our starships will likely resemble castles with thick walls, carrying an inner Earth with them. We will make our own magnetic fields and carry our ocean water as protective moats. In this way, we extend the protective womb of Earth around each off-world outpost. By doing so, we declare that even in the most inhospitable reaches, life will not only travel, it will thrive, wrapped in shields against the ancient cosmic storm. Just as our ancestors wore furs against the cold, or built roofs against the rain, spacefarers will don radiation armor in myriad forms, and thus endure and prosper under alien skies. Meglio. Life support. Build enclosed loop systems. In the tiny ecosystem of a spacecraft, every breath is precious. Exhale, and the carbon dioxide must be scrubbed away. Inhale, and you hope the oxygen you need has been regenerated. Far from Earth, the luxury of an endless open-air reservoir is gone. Instead, living in space becomes an exercise in self-contained life support, a delicate dance of recycling and renewal. To truly live in space, not just survive on supplies, we must build closed-loop systems that mimic Earth's great recycling feats on a miniature scale. On Earth, plants constantly turn CO2 into oxygen. The water cycle endlessly purifies and redistributes moisture, and bacteria break down waste into soil nutrients. Our task is to replicate those services in our spacecraft and habitats, effectively creating a tiny Earth wherever we go. The ultimate goal is often described as closing the loop, meaning all human waste outputs are converted back into inputs with minimal resupply. In a closed-loop life support system, a community could potentially live indefinitely using local resources and robust recycling without needing constant supply ships. We've already begun inching towards this aboard the ISS. The station's life support can reclaim about 90% of water used. Every drop of humidity in the air from sweat and breath, every drip of condensation, and yes, processed urine too. All are with hydrogen to produce water and methane. The water is then split via electrolysis to make fresh oxygen. This loop helps reclaim oxygen from CO2, though it's not 100% closed. The methane is vented as waste, so some hydrogen is lost each cycle. Future systems might better utilize that carbon and hydrogen. Right now, about 40% of the oxygen on ISS still comes from tanks or oxygen, supply cargo. but advanced regenerative life support aims to push that closer to 100%. NASA and other agencies are actively working on more efficient regenerative ECLSS, because for missions like Mars or a lunar base, resupply will be costly and rare. The vision is a robust system where the crew's urine can be processed not only into water, but also nutrients, where perhaps algae or special bacteria take in the CO2 and produce edible biomass or oxygen. This edges into the concept of bioregenerative life support, incorporating living organisms to do some of the recycling heavy lifting. For instance, a greenhouse module on a station could grow vegetables, yielding food, while absorbing CO2 and releasing O2, and perhaps using grey water for irrigation. Astronauts get fresh salads, and the system loops resources. There have been experiments like the Russian BIOS 3 facility decades ago, where 3 humans lived in a sealed environment sustained largely by wheat and chlorella algae they cultivated, which recycled air and water. They achieved a high degree of closure, though they still needed some external inputs. Lessons from those experiments inform today's designs. A fully closed life support system is incredibly complex. Think of all the things that must be balanced: oxygen levels, CO2 removal, trace contaminant control, water purity, nutrient recycling, temperature, pressure, and so on. On Earth, an entire planet's worth of processes handle this. In space, we'll rely on tanks, filters, reactors, and maybe greenhouses tucked into a habitat corner. It's both engineering and ecology, essentially creating a miniature ecosystem. One dramatic story that underscores the difficulty is Biosphere 2, the large sealed dome in Arizona, where 8 people attempted to live for 2 years in the early 1990s. They had an entire 3-acre biome with plants, soil, even small animals. Yet, unexpectedly, oxygen started dropping dangerously. They had to break closure and inject O2 mid-mission. It turned out the concrete in the structure was absorbing O2, something the designers hadn't fully accounted for. The biospherians also grew hungry because farming wasn't as productive as anticipated. They did survive the 2 years inside, but the experiment revealed how many hidden variables exist in a closed system. It was a reminder that closed-loop life support is hard, but also valuable, because we learned what not to do and the importance of careful monitoring of each element. In space habitats, we likely won't try to replicate an entire rainforest and ocean like Biosphere 2 did. Instead, life support might be a hybrid of mechanical and biological. Mechanical systems are very good at certain tasks, e.g., filtering water, scrubbing CO2 with chemical sorbents, and they are compact. Biological systems are good at multitasking. A plant can purify water through hydroponic uptake, generate oxygen, sequester CO2, and produce food, all in one organism, given light and nutrients. But they can be slower and less controllable. Plants might grow unpredictably or be susceptible to disease. A safe approach might be to have core mechanical systems for immediate needs and robust control, augmented by a greenhouse that contributes gradually increasing closure as it matures. For instance, imagine a Mars base. Initially, it relies on stored oxygen and water recycling units brought from Earth. But as they set up greenhouses and maybe bioreactors with algae, they start cycling more and more internally. The greenhouse provides fresh food and a supplemental oxygen flow. A bioreactor with algae could take human waste and via microbial action convert it into methane and fertilizer, or even directly feed algae that produce more edible biomass. It's a bit unappetizing to consider, but future waste treatment might literally mean turning yesterday's waste into tomorrow's breakfast. Nothing can go to waste in a closed loop. Even human solid waste might be sterilized and used as compost for crops. In the ISS right now, solid waste isn't recycled. It's packed into disposal craft that burn up in the atmosphere. On a colony, that would be like throwing away valuable carbon and nutrients. We'll want to use it. A closed loop also implies independence from Earth's supply chain. It's not just environmental closure, but also resource self-sufficiency, manufacturing spare parts on site, growing what you need. For example, rather than shipping tons of clothing, perhaps future habitats will have machines to weave fabric from plant fibers grown in the greenhouse, or recycle fibers from old clothes. These ideas blur into the economic and industrial loop closure, not just life support in the narrow sense, but they're intertwined. A truly closed system would import nothing but energy and perhaps raw materials from local sources, and export nothing but maybe excess heat or information. NASA often talks about steps. Atmospheric revitalization. We have partial closure solutions. Water recovery. We are close to full closure. Waste management. The least closed currently. But new tech like the ESA's Melissa project has multi-compartment bioreactors that break down waste and grow edible spirulina algae from it. They've demonstrated that it can work on a pilot scale, producing clean water, oxygen, and protein-rich algae from synthetic waste streams. In the coming decades, such systems might be incorporated into stations and bases. A crew might eat a portion of their protein as algae or insect meal grown from waste. Not the most glamorous diet component, but it could be efficient and healthy. Meanwhile, higher plants supply psychological satisfaction and dietary variety. One could foresee a Mars-based greenhouse with tiers, fast, growing algae in tubes, sturdy leafy greens in hydroponic trays, vine crops like tomatoes or beans twining under LED lights, maybe dwarf fruit trees if space allows for morale. Those plants would churn out oxygen and fresh flavors while sucking up the CO2 the crew produces. Water circulates between fish tanks, plant beds, and filters. In a corner, a machine quietly dehydrates and pulverizes solid waste to feed into a biodigester. Nothing smells foul because it's all well contained and managed. One hopes. Keeping odors and hygiene in closed systems is also crucial. Filters for smell are part of life support too. Life support also involves maintaining air pressure and composition. Spaceships must keep roughly sea level pressure and about 21% oxygen, 78% nitrogen. Nitrogen is inert ballast, but important, so a closed loop must conserve nitrogen as well. Fortunately, nitrogen isn't consumed by humans, but leaks could lose some. Martian atmosphere is mostly CO2 with some nitrogen. A base could extract that nitrogen to fill its habitat initially. If we master closed-loop life support, the implications are huge. It means a colony could survive even if supply lines break, which is ultimate resilience. It also means the mass burden for resupply goes way down, making deep space exploration feasible. For a trip to Jupiter that might last 5 years, bringing all the oxygen and water would be impossibly heavy. Regenerative systems make it conceivable. In the long term, as human communities settle space, their life support might become not just utilitarian, but lush. Imagine an O'Neill cylinder where the entire interior surface is basically a living ecosystem that is life support at its most advanced and pleasant, where you don't think of it as machinery at all, just an environment that naturally sustains you. But to get there, we will perfect these closed systems bit by bit in smaller stations and bases. We will learn to be gardeners of the life loop, tending to our mechanical plants and biological ones alike to keep the delicate balance. A poetic way to view it. As we leave Earth, we must carry Earth with us in our ships, not literally soil and oceans perhaps, but the essence of Earth's renewing powers. In our starships will bloom little Earths, algae as green as any forest moss, water cycling like Minnie, rainfalls in clear tubes, and machines humming like diligent microbes. We become curators of our own biosphere in microcosm. In doing so, we appreciate all the more the grand closed-loop system of our homeworld. Many astronauts, after seeing how complex and careful life support is on the ISS, remark that it made them marvel at Earth's ecosystems that do it all naturally and seamlessly. So, to live in space, we learn to bottle the sky and the sea and the soil, to make them travel, sized, and reliable. With each improvement in life support, the umbilical cord to Earth stretches thinner. One day, it may break entirely when a colony stands fully self-sufficient. And by then, that closed loop will essentially be an offspring of Earth's biosphere, a self-contained bubble of life traveling afar. Humanity's survival in space will hinge on these systems, on whether we can truly become, in effect, the ecosystem for ourselves. It is perhaps the greatest engineering and agricultural challenge we've ever undertaken. But step by step, recycling tank by recycling tank, seed by seed, we are getting there. In a very real sense, learning to live off-world is teaching us how to be better stewards of resources, which ironically circles back to help Earth too. After all, if we can recycle 98% of everything in a space colony, why not on Earth? The closed-loop technologies might one day help cities on our home planet become more sustainable as well. Thus, space life support and Earth environmentalism go hand in hand, each inspiring advances in the other. Space habitats, inflatable stations, modular cities, lunar domes, Mars bases. In the vacuum of space, or on the barren surface of another world, human habitations will be our cocoons of life. Building a space habitat is unlike construction on Earth. Here, our structures must provide not just shelter from weather, but protection from vacuum, radiation, and extreme temperatures, all while delivering air, water, and power to those inside. Over the decades, engineers and dreamers have conceived many forms for these homes beyond home. Inflatable modules that expand like balloons, modular structures that connect into orbiting cities, gleaming domes on the moon, or interlinked habitats on Mars, forming the first outposts of civilization there. One exciting development in recent years has been the testing of expandable station modules. Traditional spacecraft modules are rigid metal cans, limited in diameter by what a rocket can fare. But an inflatable can be launched compact and then expanded on site to create a far larger volume. The Bigelow Expandable Activity Module demonstrated this on ISS, packed tight during launch, then blown up into a cushioned room in orbit. It showed that fabric walls could hold pressure and withstand micrometeoroids effectively. It also proved resilient to orbital debris strikes, performing as well as solid aluminum in tests. Inflatable habitats offer big living space for relatively low mass and launch size, a huge boon for building roomy stations. Concepts like Bigelow's BA330 envisioned private space hotel modules with 330 cubic meters of volume each that could link together. NASA's earlier Transhab concept imagined an inflatable for the ISS that never flew, but the idea survived and thrives now in new designs. Companies like Sierra Space are continuing this work with their planned Life Habitat, a 3-story, tall inflatable module that could form part of a commercial space station. Inflatable stations might well become the norm, enabling something like an orbital city made of multiple bubble-like modules joined by corridors. Each module could be dedicated, one a greenhouse bubble, another crew quarters, another a laboratory. They can be added as needed, like adding extra domes to a colony of bubbles. Meanwhile, the ISS itself is the archetype of modular construction in space. It was assembled piece by piece, each launched separately and connected by astronauts. This modular approach will likely continue. It gives flexibility and incremental growth. A modular city in orbit might start with a core and then branch out with additional modules docked in multiple directions, like a growing organism. It could be reconfigurable, moving modules around or adding new arms as population grows or new functions arise. Already the ISS partners plan successors, smaller modular stations in low Earth orbit, perhaps one around the Moon. These will use standardized interfaces, akin to how shipping containers on Earth are standardized. so any new module from any participating nation or company can attach with relative ease. In future orbiting settlements, one might see a mix of inflatable habitats attached to a rigid backbone that supplies power and attitude control. On the Moon and Mars, habitats must contend with gravity, dust, and terrain. Lunar domes have long been a staple of science fiction art, transparent or opaque domes covering a habitat or even an entire colony crater. In reality, a large glass dome would struggle with radiation exposure and micrometeorites, but smaller domes or tensile fabric structures under regolith shielding are considered. One idea is to land an inflatable on the Moon, then pile moon dust over it using robotic bulldozers, essentially burying it for protection. The result might appear as a mound from outside, but inside a spacious dome ceiling, perhaps with internal lighting to feel like a sky. A lunar dome could also refer to rigid half-cylinder structures covered in lunar concrete or sandbags. European researchers have tested 3D printing with simulated moon dust and found they can create sturdy arch shapes and bricks. Imagine a lunar base where robots 3D print a thick half-dome shell on the surface. Then astronauts arrive and place a pressurized living module under that shell. Now the module is protected and can have windows that open into the interior of the dome. Mars bases similarly revolve around using local materials. Mars has atmosphere so inflatable, greenhouses might actually balloon outward there. Designs for Mars habitats often show cylindrical modules set on the ground and connected by tunnels. Picture a cluster of white or silvery cylinders, half buried in Martian soil, linked by covered walkways. Each cylinder might be a few meters in diameter and 10,015 miles long, basically an oversized railway car. Mars base plans from agencies typically start with 2003 modules landed on pre-chosen flat terrain, connected to each other. Eventually more are added, plus specialized ones. Over time, this could expand to a small village. Modularity again is key. Early bases might literally be repurposed spacecraft. NASA's concept of Mars Ice Home is an inflatable dome structure that would then be filled with water ice as a thick, transparent radiation shield around living space. A fusion of natural material and human tech, resulting in a dome that glows blue with ice, insulating the people inside. Crucially, all these habitat designs consider airlocks, how people get in and out without depressurizing the whole living area. Orbital stations have docking ports as airlocks for spacecraft and dedicated smaller compartments for spacewalkers. On a planet, airlocks are like mudrooms. One door leads out to vacuum or thin air, one leads in. You cycle the pressure in between and perhaps have a suit donning area. For the Moon, regolith dust is a menace. Apollo astronauts got their suits covered in abrasive dust, which they then tracked into the lunar module, causing irritation and equipment issues. Future lunar habitats might incorporate suit ports, basically suits that dock onto the outside of an airlock. An astronaut opens a hatch, climbs directly into the back of a suit, and detaches to go outside, leaving the dust on the suit, which stays mostly outside. Such clever innovations will shape habitat layouts. Speed of deployment is also important. An inflatable or prefab module can be set up quickly. For instance, imagine landing an autonomous habitat on Mars a year before crew. It has solar panels and starts warming itself up and producing oxygen via a reactor using Martian CO2, maybe storing it. By the time humans arrive, they have a livable ready base with stocked air and water, a pre-deployed habitat. This is the strategy of many Mars mission profiles. Send cargo and habitat first, ensure it's functioning, then send humans. The habitat might even drive itself a short distance to a better location. On Mars, using local CO2 and hydrogen brought from Earth to make water and methane fuel is planned. The same plant can fill habitat tanks with oxygen. Scaling up from small bases to true cities is a huge leap, but one can envision incremental growth, A research outpost of 6 people in 2 modules grows to 30 people in 8 modules over years. Then they build more permanent structures. Eventually, you might have interconnected lava tubes, serving as natural tunnels, housing hundreds, sealed at some points by bulkhead doors, and with farms and living quarters inside. A Martian city might mostly be underground for radiation safety, but with some skylights or surface domes with thick glass or ice for natural light in communal areas. Orbital cities like O'Neill's cylinders are further out, but remain a goal in many minds for 50,100 years ahead. Those would be kilometers long, spun for gravity, holding thousands. Getting to that scale likely requires substantial industrial presence in space. We're not close yet. Instead, nearer term we might see something like the proposed Voyager station by a private group, a rotating ring station of smaller modules accommodating maybe a few hundred tourists, essentially a big wheel with habitation pods along it. It's concept art now, but it's based on known physics of artificial gravity. If our inflatable tech and modular tech converge, building a ring out of connected inflatables might be plausible. Spin it up, and voila, a station with gravity. Lunar bases might also become more modular and city, like if multiple countries set up camps near each other. One can imagine an Artemis base camp merging with another international base, forming a little village of habitats, connected by pressurized tunnels or frequent rover commutes across the surface between them. We have to also consider support infrastructure. Power sources sitting adjacent to habitats, likely connected by cables. Landing pads a safe distance away, perhaps roads or tracks between facilities. Even something like a rail system or conveyor to bring regolith to a processing plant might appear. In short, a true habitat isn't just sleeping quarters. It's an integrated settlement with utility lines, storage tanks, garages for vehicles, and emergency shelters. One fascinating concept for Mars is the Mars Base 3D Printed Habitat Challenge by NASA, where winners designed habitats printed from Martian soil and ice. One winning design was a multi-layer dome, an outer shell of ice for radiation shielding, an inner dome of pressurized living space, and vertical silo living quarters inside with multiple levels. It looks like an elegant igloo palace. Another design featured modular pods that could be printed and connected, resembling a cluster of giant pebbles. These creative ideas all revolve around using in situ materials to expand beyond what we could bring. Dust and maintenance are also a reality. Our habitats must be robust. Everything leaks slowly. Careful monitoring of pressure and plugging of micrometeoroid punctures will be routine. Dust seals on airlocks and moving parts must be meticulous on Moon Mars, because dust can foul them. The materials of the habitat, whether layered Nextel, Kevlar, and Mylar fabrics for inflatables, or regolith-based concrete, must endure years of cosmic ray exposure and temperature swings. So, for longevity, covering habitats with soil is beneficial not only for radiation, but also to keep interior temperature stable and protect the structure from UV and thermal stress. In sum, the architecture of living in space will be an evolving blend of high-tech fabrics, metallic nodes, and native soil turned into construction material. Early on, it might look provisional, metal cans under dirt piles, or balloons inside craters. But as we refine techniques, these could morph into habitats as comfortable and secure as Earth buildings. Future generations might play soccer in a pressurized lunar lava tube illuminated by arrays of LEDs mimicking Earth daylight, or stroll through an orbital habitats park, forgetting for a moment that just meters away is the void. We humans have always adapted our shelters to environments. Think of igloos in the Arctic, clay houses in deserts, stilt houses over water. Space and other planets are new environments demanding new architecture. Our habitats will likely be modular, reconfigurable, and organic in their growth, a living architecture that starts small and builds up. They might start utilitarian, but as populations stabilize, we'll add aesthetic touches, maybe big windows with protective glass, or art and color on interior walls to break monotony. Even in a Mars base, one could paint a ceiling with a blue sky and white clouds motif to psychologically enlarge the space. One day, the phrase "home sweet home" might apply equally to a geodesic dome on Mars or an inflatable torus in orbit, as it does to a cottage on Earth. Our space habitats are the eggshells in which the fledgling off-world society will grow, initially small and fragile, but destined to get bigger and stronger. With each successful habitat, from a 2-person lunar hut to a 100-person orbital outpost, we gain confidence that we can build a home anywhere. These first habitats are pathfinders that teach us how to create shirt-sleeve Earth, like environments in places utterly alien. When future historians write of humanity's expansion, they might trace it through the lineage of our habitat designs, each more ambitious than the last, turning inhospitable wilderness into places of warmth, air, and life. Orbital stations, constant motion, speed, and the edge of Earth. High above Earth's atmosphere, orbiting stations slip around the planet at breathtaking speeds. To the astronauts aboard, however, life in an orbital station can feel strangely static, a home that continuously falls around Earth, offering an unending view of sunrise and sunset every 90 minutes. These stations are our stepping stones into space, artificial islands circling in the void at thousands of meters per second. They represent the first true attempts at living off Earth for extended periods, and they have taught us volumes about what it means to call space home. Consider the numbers. The International Space Station whips along at about 28,000 km/h, completing an orbit roughly every hour and a half. To its crew, this motion is imperceptible except by looking out the window. The ground below racing by, 16 sunrises and 16 sunsets each day. The station's microgravity environment is a direct result of this perpetual free fall around Earth. An orbital station is thus a place of paradox, tremendous velocity and dynamic movement through space, yet relative calm and stillness within. It's as if being on a smoothly flying jet, one doesn't feel the speed, only sees the world blur by outside. Orbital stations like Skylab, Mir, and the ISS have progressively grown more sophisticated. Skylab was essentially a repurposed Saturn V upper stage, a single large workshop that hosted astronauts for up to 84 days. Mir was modular, with multiple rooms docked together, and supported multi-month and even year-long stays. The ISS, a global collaboration, is the largest, about the size of a football field if you include its solar panel span. It has multiple laboratories, crew quarters, even a cupola window dome to observe Earth. The ISS has been continuously occupied for over 20 years, a testament to reliability and international commitment. It truly hugs the edge of Earth, technically still in low Earth orbit, often about 400 kilometers high, where Earth's presence is visually dominant but physically absent. Life on an orbital station is dominated by that unique setting. Constant motion, no up or down, Earth always in sight. Astronauts often remark on the overview effect, the profound shift in perspective seeing our planet as a single fragile globe. On a station, you get that view every day. One moment you see the bright blue Pacific, half an orbit later, the darkness over Africa with city lights sparkling. The thin atmosphere appears as a delicate glow on the limb, reinforcing how special Earth is. This psychological impact has arguably been one of the greatest contributions of orbital stations, how they change those who live there, instilling a deep awareness of Earth's unity and fragility. Many crew members become ambassadors for environmental protection after their missions, precisely because, from their vantage point, they saw the paper, thin atmosphere shielding all life. Stations move fast and also experience microgravity permanently. We've discussed how microgravity affects the body. Here, we consider how it defines the habitat and daily life. It's as if being on a smoothly flying jet. One doesn't feel the speed, only sees the world blur by outside. Orbital stations like Skylab, Mir, and the ISS have taught us how to live in perpetual free fall. Daily life on a station is regimented, yet surreal. Astronauts float from module to module, tacking their toes under handrails to stabilize themselves at work. There is no true up or down. They might sleep in a vertical orientation and work on a wall. They learn to orient by agreements. The station's layout becomes a three-dimensional maze, with air vents quietly whooshing, equipment humming, and laptops velcroed to surfaces. Constant motion means constant microgravity, which shapes every mundane task. Drinking requires sealed bags or straws. Salt and pepper come in liquid form to be sprinkled. And cleaning involves chasing down every crumb and drop that could drift into electronics. Even something as simple as cutting hair is an operation. One crew member uses clippers attached to a vacuum hose to suck away the snipped bits of hair, lest they flit about like dandelion seeds in the cabin. Though busy with science and maintenance, station dwellers make time to appreciate their unique vantage point. In the ISS cupola, a multi-windowed dome looking down at Earth, astronauts gather like souls at a campfire, except their fire is the radiant planet below. They press their faces to the windows to watch thunderstorms flicker, auroras shimmer in green ribbons along Earth's atmosphere, and familiar continents slide past under day and night. Many describe moments of floating there in silence, awash in awe and homesickness all at once. On the edge of Earth, they become keenly aware of its beauty and fragility. One can imagine future orbital citizens experiencing the same daily wonder, waking up to a sunrise that covers the whole horizon in seconds, or pointing out to a child where their grandparents' country is as it comes into view far below. Orbital stations must also constantly mind their environmental systems. Crews on the ISS spend hours maintaining life support equipment, swapping CO2 scrubber filters, fixing the water recycler. They live with the awareness that just a thin hull separates them from the vacuum. It's a safe home, but a tended home, one that demands vigilance. When a warning alarm rings, everyone stops and responds methodically, checking pressure readings, donning emergency masks if needed. Drills are run for fire or ammonia leaks. In 2 decades, serious emergencies have been rare, but crews train relentlessly for them. This is part of life in an orbital outpost. You become not only a resident, but also a constant caretaker of your habitat. In the future, perhaps more systems will be automated or built with redundancy to ease this burden. But likely, station crews will always have some janitorial duties for their floating colony. One day, orbital stations might transition from research bases to commercial hubs or even tourist destinations. Designs like a rotating hotel with artificial gravity at its rim have been proposed, as well as free, flying private stations composed of inflatable modules. In those, everyday life might incorporate more leisure, perhaps a space lounge with a wide window where guests sip beverages from magnetic cups while gazing at Earth, or a small zero-G sports arena where humans can experience graceful somersaults and games of three-dimensional tag. What is constant is the backdrop of speed and Earth's curvature. Even for a tourist, the first time they unstrap and float freely must be astonishing. The body initially panics with a sensation of falling, but then delight takes over as you realize you can fly from one end of the habitat to the other with a gentle push. Laughter, we can imagine, will echo through future orbital halls as newcomers bounce around like children in a playground, finding the sheer joy in microgravity motion. Communication on orbital stations is near instant with Earth. Crews talk daily with mission control. They even make IP phone calls or video links to family. This closeness in comms and relative proximity maintain a strong bond with home. They know if something goes very wrong, a Soyuz, or Dragon capsule can bring them back to Earth in a matter of hours. Orbital living is thus a liminal state, neither fully on Earth nor fully away. It's perhaps akin to living on a ship in sight of shore, distant but not isolated. As we move outward, stations around the Moon will lengthen that tether, a few seconds delay in communications, and days of travel from Earth. Eventually, a station orbiting Mars would be truly frontier, 8-month travel time to reach, and radio signals taking 10 to 20 minutes one way. By then, an orbital station might have to be more autonomous, a self-sustaining community. For now, the ISS remains humanity's shining example of a sustained home off Earth. It circles endlessly, a bright star crossing twilight skies if you know when to look. Many people on the ground have stepped out to wave at that moving dot, knowing human beings are up there. Inside, those humans might at that moment be having dinner, squeezing mac and cheese from a pouch and rehydrating a tortilla, maybe playing music on a guitar. They might be joking with a crewmate about a glitch they fixed earlier, or planning tomorrow's science tasks. Perhaps someone is writing in a personal journal by the dim reading lamp, recording feelings for which there are no easy words. Over the years, journals from space have revealed how much astronauts ponder existence, miss their families, revel in the view, and even dream of floating. Some report they still dream they are weightless after returning to Earth. The orbital life has its own rhythms: work, exercise, rest, all carefully scheduled, yet the extraordinary lurks at every window glance. Looking ahead, we see orbital stations growing more permanent and populous. We might go from 6-person crews to 50-person communities in large rotating habitats by mid-century. These could become the first true space settlements, with engineers, scientists, teachers, maybe even artists or caregivers living on board for years, potentially raising families in orbit. The line between spacecraft and colony will blur. Already, the ISS is an international village of sorts. Russians, Americans, Europeans, Japanese, Canadians working and living together in a tight space, sharing meals and stories. In the future, orbital communities may develop their own micro-culture, unique slang, celebrations of station milestones, maybe even traditions like an orbital sunset party every Friday where residents gather to watch a particularly beautiful sunset and play music. Such a life is not for everyone. It requires tolerance for confined quarters and distant horizons. But those who do live there often describe it as profoundly fulfilling. Every day, I looked out the window and saw something that made me grateful to be alive, one ISS veteran said. Another confessed that returning to Earth's gravity felt strange and constraining. They had adapted so well to fall freedom that walking was almost disappointing. From these anecdotes, one gleans that constant motion in orbit leads to constant adaptation. Humans truly learn to live anew, and live they do, not just exist. They find camaraderie in their crew, beauty in their tasks, and a sense of participating in a grand human endeavor. An orbital station is more than a lab. It is a community in motion, forever voyaging around our world and reminding those on board that home can be wherever we build it. Moon bases: dust, light, and permanence. On the dusty plains and crater rims of the Moon, humanity envisions its first footholds beyond Earth. A moon base would be our initial attempt to live permanently on another celestial body, a place with gravity, soil, day and night, yet utterly alien and inhospitable. The challenges of the Moon are distinct: the peculiar daylight cycle, the pervasive razor-sharp dust, and the question of how to make a settlement truly permanent in a place long thought of as desolate. And yet, the Moon offers tantalizing advantages: nearby resources like water ice in shadowed craters, a quiescent geology, and proximity to Earth that makes it the logical training ground for further outposts. One of the Moon's greatest challenges is its dust. The lunar regolith is not like soft Earth sand, without water or air to weather it. Each particle is jagged, gritty, and sticks to everything. The Apollo astronauts discovered this to their dismay. After bounding about on the surface, their suits were coated in fine grey powder that smelled like spent gunpowder and clung stubbornly. The dust worked its way into suit joints and seals, causing wear. Some astronauts suffered lunar hay fever, with sneezing and throat irritation when they inhaled the dust carried into the lunar module. Future moonwalkers in a base will likely face the same nuisance amplified because they'll be doing hundreds of EVAs, not just a few. Mitigating lunar dust will be crucial. Engineers have plans, spacesuit airlocks or suit ports to keep dust out of habitats. Also, cleaning protocols might involve using electrostatic wands or brushes to push dust off suits, or sticky mats at airlock entrances to capture particles. The base interior could be maintained at slight positive pressure so that if there's any leak, air flows out rather than dust blowing in. Additionally, the living quarters might be elevated or isolated from the surface, for instance, connected by enclosed tunnels to minimize direct contact with dusty ground. However, dust will inevitably find a way in. Thus, materials inside the base must be chosen to resist abrasion and be easy to wipe down. Air filtration systems will constantly scrub floating particles. Moon dust is not toxic in itself, but over long exposure, it could cause lung issues. So base design treats dust almost like a hazardous material to be carefully contained. Despite these challenges, no one suggests avoiding the moon due to dust. Rather, we adapt as explorers always have. We will likely deploy simple solutions like regolith, covered garages for rovers, where they can shed dust away from the main habitat. Next is the matter of light and darkness. Unlike orbit, where the sun rises every 90 minutes, on the moon, a day lasts 29.5 Earth days. At the equator, that means roughly 2 Earth weeks of blazing sun, then 2 weeks of frigid darkness. The temperature swings are enormous: 120 degrees in day, 170 degrees at night. Surviving the night is a major design hurdle. It requires either storing ample energy or having a nuclear power source, as solar arrays produce nothing during the long lunar night. One solution is to establish bases near the poles, especially the South Pole. There, due to the moon's slight axial tilt, some mountain peaks receive near, continuous sunlight. This is a boon for solar power. Farms of solar panels on ridges can bask almost all month, needing minimal batteries. Likewise, some craters at the poles remain in permanent shadow and trap ice. So at the South Pole, you have 2 vital resources side by side: sunlight and water ice. That's why current plans target the South Polar region for a base. If you set up on a well-lit ridge, you can tap constant power and endure no long nights. Even with abundant sunlight, the angle of light is shallow, casting long, eerie shadows. A base might get sunlight at a low slant, which could complicate things like charging batteries or heating certain sides of habitat. But engineers can arrange rotating solar panels or mirrors to direct light where needed. The pole offers relative thermal stability too. In perpetual light areas, temperature stays around a constant 50 to plus degrees range, easier to manage than the equatorial swings. Still cold, yes, but a base can be insulated and warmed with sunlight. One imagines a polar moon base perched on a crater rim, the landscape bathed in a near, constant dawn, like glow. Surrounding the habitat are glittering solar arrays on tall masts that rotate to face the sun. Cables snake from these arrays to modular shelters buried under regolith for radiation shielding. Nearby, maybe just a few kilometers down, slope in shadow, robotic miners scoop up regolith and ice chunks from a crater floor, hauling them to a processing plant. There, the ice is melted and split into hydrogen and oxygen, rocket fuel, and also water for the base. At times, humans might go down to assist or set new explosives to break ice, but likely much of that work is automated to keep astronauts mostly in the light and out of extreme cold. Radiation on the moon is a concern due to lack of atmosphere. As discussed earlier, thick shielding is needed for full protection long term. Covering habitats with moon dirt is the simplest approach. Designs show cylindrical or dome habitats buried under several meters of regolith, perhaps placed inside excavated trenches or pits to make burial easier. This has the side benefit of protecting from micrometeorites and insulating against temperature changes. A buried lunar habitat might not have windows, but perhaps periscopic devices or external cameras can bring in views. Alternatively, some sections could be left unburied and use water-filled walls or special plastics for shielding transparently. For example, a greenhouse might be a dome with double walls filled with water, letting in sunlight but stopping radiation. By using local water for that, we leverage resources. Permanence on the moon involves building infrastructure that doesn't need frequent Earth resupply. If we can harvest lunar water, grow some food, and manufacture building materials, a base transitions from outpost to settlement. Astronauts living there would shift from just surviving to thriving. They might plant hardy plants in lunar soil. Imagine a small lunar greenhouse with rows of leafy greens under LED lamps, a splash of life in the grey. One day, lunar settlers may cultivate the beginnings of a lunar society. Perhaps they start marking the passage of time differently. One lunar day, night cycle is a month, so they might have unique holidays at each full Earth to give hope during darkness, or at each sunrise to celebrate renewal. The concept of day and night is tricky there. At poles, perhaps they forget night altogether. Will they count time in Earth days or adapt to a lunar day of 708 hours? Likely they'll stick to Earth days for convenience with communications, but local timekeeping might develop for tasks. The moon's low gravity is another interesting aspect. Astronauts on Apollo enjoyed hopping high and carrying heavy equipment more easily. Over long term, though, we don't know how human health fares in 0.16 G. It's more than microgravity, so bone loss and muscle loss might be slower, but it's still much less than Earth. Moon settlers may need robust exercise regimes and perhaps artificial gravity chambers. There's an idea to set up a short, radius centrifuge on the moon for sleeping quarters, spin people gently at night to simulate full gravity on their bodies, allowing better bone maintenance. It might not be comfortable, but it's being studied. Nonetheless, the moon's partial gravity could be a fascinating middle ground, enough to walk and keep some bodily orientation, but light enough to perform feats of strength and agility impossible on Earth. A child growing up on the moon might become used to bounding meters high without fear, playing low-gravity sports that Earth-born kids could only dream of. But if that child came to Earth, he or she might find our gravity oppressively heavy and struggle physically. We may see one day the ethical discussions about raising people in low gravity, knowing they might never be fully adapted to Earth. Permanence also means governance and routine. A moon base, after a decade, might have a rotation of crews like a scientific station, or might start keeping certain pioneers long-term. Over time, they might form a council to manage resources, plan expeditions to new craters, coordinate with Earth, but increasingly make independent decisions due to their on-site expertise. The moon is close enough that Earth oversight will be strong initially, but as the base grows to a settlement of dozens, a degree of autonomy likely blossoms. The identity of lunar inhabitants may shift, no longer just visitors, they become lunarians, with pride in being able to live in a place no human could before. They might develop an affinity for the stark moonscape, the black sky even at noon, the brilliant stars unblinking in absence of atmosphere, the sight of Earth hanging always in the sky. The Earth rise that wowed Apollo 8 astronauts isn't seen at the poles, but at equatorial bases, Earth would rise and set slowly over the month, a huge blue marble appearing and disappearing. Watching Earth set might be tinged with homesickness for some, but also a reminder of purpose. They are humanity's advance party, staying even when Earth is out of view for 2 weeks, proving we can endure off-world. A permanent moon base will likely accumulate the detritus of ongoing life. Old habitats might be repurposed as storage, spent landing vehicles turned into additional shielding, or cannibalized for parts. Over years, a sort of lunar town might emerge, with pathways worn in the regolith from frequent rover trips, maybe a little mound marking where the first flag and plaque were placed, now part of a larger complex. The base might honor that spot as a historical monument, even as they erect newer, larger structures around. There could be a cemetery one day, if someone chooses to have remains interred on the moon, a truly permanent resting place beyond Earth. All these are signs of moving from temporary exploration to true settlement. The moon's close connection to Earth means it will always be a bit of an extension of Earth, not wholly separate like Mars. Yet making a permanent human presence on the moon will profoundly change our species. No longer will all humans live on one world. We'll have a small population on another, living year-round, raising national flags, or perhaps a unified lunar flag, creating the first off-world community. They'll tackle everyday problems like how to fix a broken regolith excavator, or how to get fresh coffee when the Earth shipment is delayed. In solving these, they set the template for Mars and beyond. Someday, perhaps the moon base will grow into a moon village, with multiple habitats from different countries or companies near each other, connected by pressurized tunnels or frequent rover traffic. An international zone of cooperation on lunar soil, scientists sharing labs, tourists coming for long stays in special guest modules, mining operations selling propellant to passing spacecraft, maybe a radio astronomy outpost a short distance away on the far side. The moon could host not just one settlement, but a network of them, each specializing. One near a large ice deposit becomes a fuel factory. One at a peak of eternal light becomes a power station. One in a lava tube becomes a research park shielded from radiation by meters of rock. In all these visions, we see the moon transforming from a dead rock to a place of human footholds. Lights glowing softly at Shackleton Crater's rim, tracks leading out across the powdery desert to points of interest, radio voices chatting in multiple languages across the lunar network. And above any one base, if you step outside and look up, you see Earth, colorful, beckoning, full of life, a reminder of home and why you're extending its reach. Many lunar explorers have noted the profound emotion of seeing Earth from the moon's surface. It appears small enough to cover with your thumb held at arm's length, a fragile ball in darkness. That perspective might become routine for residents. They glance at Earth to check the weather patterns, or just as we glance at the moon from Earth. Maybe they have a saying like, "Earth's almost full tonight, beautiful and bright." The fragility of Earth will be obvious to them, likely instilling a strong sense of environmental stewardship and unity. After all, when you live on the moon, national borders on Earth literally disappear. You see the wholeness. Dust, light, and permanence. The moon will test our ingenuity with each. But where we solve those, we turn a forbidding environment into a second home. And as we plant roots there, even shallow ones, we become a multi-world species. The first moon base's success will be a signal that humans can truly stay somewhere other than Earth, not just plant a flag and leave. It will be one of our civilization's greatest milestones, the moment we go from sailing to a new shore to building a village there that can thrive through the changing seasons of that new world. Mars colonies, isolation, storms, and stability. When we imagine living on Mars, we conjure a vision of rust, red skies, sprawling dusty plains, and perhaps a small cluster of habitats huddled against the cold. Mars has captivated human imagination like no other planet. It is the world most like Earth in our solar system, yet still profoundly different. To establish a colony on Mars is to commit to isolation far greater than on the Moon, to face alien weather and planet-wide dust storms, and to seek stability and self-reliance in an environment that offers little mercy. It is, in a sense, the ultimate test of whether we can truly become a multiplanetary species. One of the most striking features of Mars is its isolation. At closest approach, Mars is about 55 million kilometers from Earth, At furthest, over 400 million. Even at light speed, messages take anywhere from 4 to 22 minutes to travel one way. This means a colonist on Mars who asks a question of mission control must wait perhaps half an hour for an answer. Effectively, they operate without real time support. Emergency on Mars. The crew must be their own first responders. Help from Earth would arrive, at best, months later, via supply rocket. The psychological effect of this distance is profound. Mars settlers will look up at night and see Earth as a tiny star, a pale blue point of light. There will come a moment, perhaps, standing under the Martian sky, when one realizes that everything familiar is a mere glimmer in the heavens. The emotional fortitude required to not feel crushing. Loneliness at that realization must be considerable. Yet, as humans often do, colonists will likely find ways to cope. Ritualizing communication sessions, fostering extremely tight, knit community bonds amongst themselves to replace the broad social network left behind, and cultivating a sense of purpose that justifies the distance. We have some analog in Antarctic winter crews who endure months of isolation and darkness. Mars will be that magnified, plus no immediate rescue possible. Crews on Mars will certainly deal with bouts of homesickness, interpersonal tensions from being in a small group so long, and perhaps an existential loneliness of being literally on your own world. In anticipation, our selection of Mars colonists will emphasize psychological resilience. Over time, as a colony grows and includes more people, that isolation lessens internally, but externally it remains. They are all isolated together from Earth. Eventually, a new normal sets in. Mars is home, Earth is the distant land. Children born on Mars might not feel isolated at all. For them, Earth might be an abstract concept, a beautiful star that their parents talk about. They may form a strong identity around their Martian homeland, bonding with their fellow colonists as one people in a way we haven't seen since perhaps early island settlers on Earth. The environment of Mars poses unique trials. Dust storms are iconic of Mars, vast clouds of fine dust that can engulf the entire planet. These storms can last weeks and obscure the sun, plunging the surface into a dim orange twilight. For a colony reliant on solar power, a global dust storm is a serious event. Energy rationing might be necessary unless nuclear reactors or massive battery farms are in place. The dust is pervasive. It can creep into machinery, abrade seals. The Martian dust storm of 2018 was so massive it ended the Opportunity rover's 15th-year mission by blotting out sunlight for too long. A crew on the ground would have to hunker down for possibly a month of low power, limited EVA, and carefully filtered air intake to avoid dust contamination. They might see the sky turn butterscotch brown and the sun become a feeble glow. Outside, the wind, though thin air, can still loft particles and slowly sandblast exposed surfaces. Colonists would design habitats with storm lockdown modes, shutters over critical windows, extra sealing on airlocks, and perhaps electrostatic repellents on solar panels or dust-resistant coatings. They might plan their heavy activities for clear seasons. The unpredictability of storms adds a psychological challenge. You could wake up to find the world has gone dark, and your carefully scheduled week must be thrown out to deal with nature's interruption. Flexibility and robust contingency plans are a must on Mars. Even when not stormy, Mars is cold and arid. Average temperatures hover around 60 degrees, though midday at equator can be a comfortable 20 degrees Celsius. The thin atmosphere offers scant protection from radiation or meteorites. Stability for a colony means building burrows or thick-walled habitats, likely underground or covered, similar to the Moon. Many concepts involve Martian lava tubes, natural tunnels left by past lava flows, as ready-made caves that could be sealed and pressurized. Imagine an entire colony built inside a cavernous lava tube. You'd have a rock ceiling, 30 meters high shielding you, and you could construct habitats and greenhouses in relative safety. Mars has gravity is 0.38 g, which is perhaps enough for easier mobility than the Moon, and possibly healthier long-term, but still, we don't know if 0.38 g is sufficient to prevent muscle atrophy and other issues. Martians might also need centrifuge habitats to simulate Earth gravity part-time. Over generations, perhaps humans could even biologically adapt somewhat to 0.38 g, but that's speculative and slow. Building a stable society on Mars entails getting beyond survival mode. That means reliable life support. Early on, Mars crews will eat mostly Earth, shipped food supplemented by some fresh greens grown in hydroponic trays. Over time, as they cultivate more, a larger portion of diet comes from local produce. Perhaps they'll manage small farming experiments in Martian soil. They might enjoy root vegetables, leafy greens, even Martian strawberries one day, grown under pink LED lights in climate-controlled domes. The first time colonists eat a meal made entirely from Martian, grown ingredients will be a huge milestone, a taste of self-sufficiency. Martian colonies must also deal with distance and self-governance. With hours of com delay round trip, they cannot be micromanaged by Earth. A certain autonomy is inevitable. We can foresee that once a group of humans has lived on Mars for, say, a decade, handling their own emergencies and decisions, they will start to feel Martian, not just physically, but politically. They might wish to govern their colony's affairs with less Earth intervention, not out of disloyalty, but practicality and identity. This parallels how remote colonies on Earth eventually sought independence or self-rule. The seeds of Martian societal culture will grow in those first enclaves. They might create new holidays. They may develop new art, imagine dust drawings or sculptures from native rock. Music might be cherished in the long confined days. Perhaps someone brought a compact electronic keyboard or guitar, and evening gatherings include singing songs with new Martian lyrics about the landscape or longing for Earth. Over time, unique traditions will emerge. Storms and isolation may foster spirituality or philosophies tailored to Mars. In the extreme isolation of the Antarctic winter, crews sometimes report a heightened sense of fellowship or existential reflection. On Mars, this could be even stronger. There could be ceremonies before a long communications blackout, or communal readings of Earth literature to feel connected. Or something novel, perhaps stepping outside during a dust storm in a safe location to experience Martian night in a symbolic way. These cultural adaptations, small at first, lay the foundation for a stable society that's more than just surviving. It's living fully on Mars, with meaning and community. Loneliness will certainly be an enemy. Even a group of, say, a dozen, could feel claustrophobically small after a year together with no one else to see. Colonists will lean on technology, immersive VR calls with loved ones. Perhaps they'll have AI companions or robotic pets to provide some variety. They might maintain robust social schedules, designated game nights, shared cooking experiments. These efforts sound trivial, but they could be the glue that keeps spirits up during the monotonous stretches. The colony might rotate duties not just for fairness, but to break monotony. Everyone gets a turn at greenhouse care, at rover driving, at lab analysis, etc., preventing boredom and over-specialization stress. Mars also faces risk of cabin fever and interpersonal conflict magnified by isolation. To manage this, a Mars colony charter might include conflict resolution protocols, possibly trained mediators among the crew, or the ability to have private space. Over time, as populations grow, people will be able to find friend circles or get space from those they clash with, as happens in any town. The early crew of 4006 doesn't have that luxury. Later colonies of 50+ will. If the colony endures through its first few tenuous years, it will accumulate improvements, larger greenhouses, an expanded habitat with spare rooms, maybe even the beginnings of terraforming on a small scale, like creating a pressurized dome with a garden where you can take off your suit. This wouldn't terraform Mars globally, but it creates micro-environments of Earth, like conditions to enjoy. Think of a Mars biodome as a park. Colonists could go in and smell moist air, feel grass underfoot, and have a picnic under an artificial sky of lights. Such an oasis could be mentally therapeutic, a stability factor for society. Mars stability as a colony also involves economics. What will sustain it materially? Initially, heavy support from Earth, funded by exploration budgets or billionaire ventures. Eventually, the colony needs to produce value, be it scientific discoveries or facilitating further exploration. A stable Mars settlement might become a hub for the inner solar system trade, extracting useful minerals or manufacturing components in its lower gravity that are then shipped outward. If the economy stabilizes, the colony can grow, inviting more settlers because now it's not merely a cost center, but has industries. Family migration might happen. Perhaps a scientist brings spouse and children to live on Mars for a multi-year research project once the base is safe enough and voluminous enough. That moment, children laughing in a Mars habitat, will signify a colony crossing from expedition to community. The ultimate stability is generational. When the first person who was born on Mars grows up on Mars, knowing no other world as home, that person's identity will be Martian fully. The social dynamic then shifts. You have natives and Earth-born immigrants. Natives might adapt physically to Mars. They may see Earth as foreigners, albeit ancestral ones. It's easy to foresee a strong Martian patriotism or local pride developing. When enough people and infrastructure accumulate, they might declare themselves a Martian colony in political terms, perhaps seeking recognition not as under Earth nation jurisdictions, but as a new society. How that plays with terrestrial authorities will be interesting, likely new governance frameworks. Ethically, should Mars be an escape for humanity or a branch? These big questions will come into sharp relief when a Mars colony proves it's here to stay. Mars also offers unmatched adventure for colonists. They can pressurize rovers and drive hundreds of kilometers exploring canyons like Valle Marineris or climbing Olympus Mons. On rest days, some might venture out in pairs to examine odd rock formations or simply enjoy the horizon, with safety protocols, of course. The freedom to roam an entire planet can give a sense of frontier akin to early settlers on a continent. Over time, these explorers might set up secondary outposts, a mining camp here, a science station there, each seed a future settlement. That's how a colony expands stable, outgrowth and linking back. Maybe a base at a polar ice cap to harvest pure ice, or one near a volcanic region for geothermal energy. Throughout all, stability is about adaptation. Mars will change the colonists even as they change Mars. They will adapt routines to Mars's day, which is 24 hours, 39 minutes, only a little longer than Earth's. So we picture a Mars colony after a generation, a cluster of habitats at a site like Utopia Planitia, or near a large ice deposit. There are maybe 200 people. They have a town name for sentiment. Perhaps they call it Bradbury or Asimov, or an indigenous word meaning new hope. They have greenhouses providing a large fraction of their food. Diets lean vegetarian with occasional lab, grown meat, or insects for protein. They wear light indoor clothing, but always keep a pressure suit handy in case of depressurization emergencies. They have built radiation storm shelters underground, where they retreat during rare solar flares. They operate a fleet of rovers and even hoppers to reach distant locales. A handful of children play in a centrifuge playground that simulates Earth gravity for exercise and fun. Education is mostly via digital content from Earth, but with local teachers adapting it. When the sun sets, the domed common area lights up with a warm glow. Perhaps the colonists gather for dinner in a communal mess, sharing news, a new baby born, a scientific breakthrough in the lab, the successful test of a new water, recycling system that will allow more crops. Someone pulls out a guitar or a flute brought from Earth and plays a gentle tune. Others join in song or just listen, reminiscing about stargazing on Earth or plans for their next expedition on Mars. Outside, the wind may whistle and dust may skitter, but inside, it's shirt-sleeve comfortable and convivial. These people have carved out a stable life on an unstable world. Isolation, storms, and initial hardship have given way to routine and resilience. This colony is still tightly bound to Earth for certain supplies, but it's inching toward independence. They've even started making their own bricks and expanding living space without needing Earth shipments. Morale is cautiously optimistic. They are living the dream of many centuries, humans on Mars, and they feel the eyes of humanity on them. They have bad days, conflicts, homesick crying nights, technical crises, but they overcome them one by one. Each solved problem is a step toward not just surviving, but thriving on Mars. Someday, one of them steps outside on a clear dawn and watches the sun peek over the ruddy horizon. They see, faintly in the sky, a bright star, like dot that is Earth. At that moment, perhaps they realize, we are the ancestors of a new world. The storms will come and go. The isolation is real, but so is our community. And with each passing soul, Mars is becoming more stable as a human home. What was once a far-fetched science fiction scenario is now, under their feet, red reality, harsh and beautiful. And in their hearts possibly grows a fierce love for Mars, forged by facing its extremes. Just as people love their Earth homelands, from deserts to Arctic tundra, because it's theirs, so will Martian colonists love the rust and dust of Mars. In that love lies the true seed of a stable society, one that will endure and eventually flourish. Deep space, generation ships, and the dream of interstellar travel. Beyond the planets that circle our sun stretches the vast gulf to the stars. For ages, humans could only wonder what it would take to cross that unimaginable distance. Now, as we build habitats in orbit and envision colonies on Mars, a further dream glimmers on the horizon, voyaging to another star system. Such a journey would be measured not in days or months, but decades or centuries, far longer than a human lifespan. To accomplish it without breakthroughs in physics, we have conceived the idea of the generation ship. A self-contained world, carrying multiple generations of people who live and die during the voyage so that their descendants might one day arrive at a new sun and new Earth. It's a concept where science fiction edges into serious scientific discussion, because while daunting, it does not defy known physics, only engineering and human limits. Imagine a spacecraft, perhaps a few kilometers in length, a rotating cylinder or torus providing artificial gravity inside. It is essentially a miniature Earth, complete with gardens, water systems, and an internal sky. Such a ship would depart Earth with a population of, say, a few hundred or thousand, and an entire closed-loop ecosystem to sustain them indefinitely. The logic of a generation ship is straightforward. If we can't get there fast, we go slow and take our time with life continuing aboard. It turns interstellar travel into a multi-generational project, much like ancient human migrations, where those who set off never saw the destination, only their descendants did. The challenges are enormous. The ship must be practically self-sufficient in resources for centuries. This means near-perfect recycling of water, air, and nutrients. It must have reliable power, likely a fusion reactor, or a large solar sail catching distant sunlight. It needs to be shielded against cosmic rays, perhaps a magnetic field or heavy shielding, or both, because over a lifetime, cosmic radiation could otherwise severely harm the crew. Then there's the social challenge. How to maintain a stable society in a closed vessel for many generations. Humans in isolation can have conflicts. How to avoid destructive strife that could sabotage the mission. Perhaps a strong common purpose and carefully managed governance structure would be crucial. The crew's descendants must be educated in the ship's maintenance and in the mission goal, so that by the time the ship nears a target planet, they have the knowledge to land or settle it. The culture aboard may evolve in unforeseen ways. They might develop new religions or philosophies about their unique existence. They might even forget Earth if records were lost, or deliberately reinvent their history. There's a well-known fictional trope of generation ships that lose knowledge of being on a ship. Realistically, we'd guard against that by ensuring continuous education, and maybe having parts of the ship transparent, so people can always see the stars outside and remember they are on a journey. In fact, imagine stepping to an observation dome on a generation ship. Outside is not Earth's blue sky, but the black of interstellar space, studded with ancient light. The stars barely change position over decades, though the destination star gradually brightens over generations. To the people on board, those stars are their night sky, constant and comforting. A generation ship would likely depart slowly from Earth, maybe assembling in orbit or near the moon. Families and skilled individuals would board with solemn farewells, knowing they will never return and possibly never even see the new world. But their great-grandchildren might. It is a massive leap of faith and commitment. Perhaps they are driven by necessity or by pure exploratory zeal, a willingness to sacrifice personal horizon for the species' expansion. During the voyage, life on a generation ship might in many ways echo life on a large space colony, with agriculture, work, birth, death, art, and routine. They'd celebrate their ship's anniversaries as we celebrate national holidays. There would be time to pursue studies, hobbies. After all, in a self-contained town, traveling in darkness, cultivating culture is vital. They might develop unique art forms suited to weightlessness or confined space. Perhaps zero-G dance performances in a central hub, or music using instruments crafted from spaceship materials. Over centuries, their language might drift from Earth's, picking up spaceborne slang and technical vernacular, becoming a dialect or even a distinct language by journey's end. Anthropologically, a generation ship is a fascinating petri dish of society. Small, isolated, forced to be self-reliant and balanced. Social engineers might, when launching, try to include a broad genetic and cultural diversity to avoid inbreeding or cultural stagnation. The early crew might have multiple languages, beliefs, traditions, intentionally, so that the future culture aboard is rich and adaptive, not monolithic. Because a homogeneous group might handle conflict resolution worse or could face genetic issues down the line. So, one imagines the ship launching with couples and families from many backgrounds, all united by a mission charter, somewhat like the US Constitution, a guiding document that lays out rights, responsibilities, and conflict resolution methods for the community that will persist long after the original authors are gone. Technologically, generation ships flirt with extremes. Speeds of a few % of light might be attainable with advanced propulsion. Even then, reaching Alpha Centauri at 1% of light speed takes about 437 years. If they average 5%, it's 90 years, possibly within one long lifetime, but more likely spanning 3 or 4 generations. Many proposals consider hundreds of years voyages. This demands reliability far beyond any machine we've built. Perhaps the ship will have onboard manufacturing to replace or repair parts. It essentially must be a self-healing system or carry massive redundancy. The voyagers might also enter stasis or sleep to shorten perceived time. But generation ship concept typically assumes they remain awake and society continues. Interestingly, the generation ship idea, while heavy on logistics, is also inherently hopeful. It assumes that even if individuals can't reach a goal, the chain of humanity can existential hope and insurance for humanity. Stephen Hawking and others argued that, to ensure our survival, we eventually must spread to other star systems. Generation ships could be our way to do that, with known physics. They are effectively space, going Noah's arks, carrying not just humans, but seeds, embryos, knowledge, possibly even animals to plant life elsewhere. It's a massive undertaking, building a world to travel between worlds. As of now, this remains theoretical. The farthest humans have gone is the Moon. Even Mars is still ahead. But as we master each step, orbital living, lunar and Martian bases, the generation ship idea moves from wild idea to distant but conceivable project. Already groups like Icarus Interstellar and the Initiative for Interstellar Studies have begun research on how to design life support and propulsion for such century-spanning missions. It might be a project of a civilization, not a single country, something humanity collaborates on when we feel confident enough in our space capability and united enough in purpose. Perhaps a future Earth that is sustainable and peaceful might devote some of its energy to launching world ships to nearby stars. What's inspiring is that generation ships treat life itself as the Voyager. It's not a quick heroic exploit by a few, but a commitment of an entire living community to journey together into the unknown. In a sense, it's a continuation of the earliest human story. Tribes migrating across continents, not knowing what's ahead, but believing somewhere fertile and safe lies beyond the horizon. Only now, the horizon is interstellar space, and the journey dozens of lifetimes. It asks, can we create meaning and maintain society in the ultimate closed bubble? If the answer is yes, it affirms a wonderful adaptability of humans, that we can find home even in the journey, not just the destination. So while generation ships remain for now a bold speculation, they encapsulate the enduring human traits of wanderlust, patience, and hope. One day, a child might be born in the midst of such a voyage, never having stood under an open sky, yet that child may live to step onto a virgin earth under an alien sun, fulfilling a dream begun many generations before. That prospect, that we might traverse the cosmic ocean as families over epochs, gives a sense of how far our will to explore could truly take us. It lets imagination orbit physics, daring to plan for futures far beyond our personal lifespans. In this way, generation ships are both engineering challenges and profound statements of optimism, an implicit faith that humanity will endure and carry forth its flame of life to new worlds among the stars. Terraforming, reshaping worlds. If one day we stand on Mars or another barren planet and yearn not to be confined to domes and suits, the thought arises, could we transform this world to be more like Earth? Terraforming is the grand idea of planetary engineering, modifying an entire planet's environment to make it habitable for Earth life. It is an idea at the intersection of high science and audacious imagination, because it implies taking what nature built over eons and tweaking it intentionally on a massive scale. The most discussed target is Mars, since it has water ice, some CO2, and was possibly warmer eons ago. The dream, thickening its atmosphere, warming it, and perhaps even seeding it with life, so that future generations might walk on Mars without a spacesuit, under a blue-ish sky with flowing water around. But how feasible is this, and what are the ethics? Mars today has an atmospheric pressure less than 1% of Earth's are, too thin to breathe or to allow liquid water stable on the surface. It's also cold. The basic terraforming plan would be to pump up the pressure and heat by releasing greenhouse gases, mainly CO2, which Mars has locked in polar ice caps and soil. If we could vaporize the poles and some CO2 from the soil, we'd create a thicker atmosphere that could trap more heat. Some scientists once thought there was plenty of CO2, but recent studies, including findings from NASA's MAVEN orbiter and Mars Express, indicate Mars simply doesn't have enough accessible CO2 to do the job. If you sublimated all known CO2 on Mars, you'd get only perhaps a 15 from 30 mbar atmosphere. That's nowhere near enough for humans or to significantly warm the planet. A 2018 Nature astronomy paper concluded that there is not enough CO2 remaining on Mars to provide significant greenhouse warming where it released. Even massive future efforts would result in only a fraction of the pressure needed. In short, current research puts a damper on classic terraforming. Mars is too CO2, poor to be easily terraformed with present tech. That doesn't make it theoretically impossible, but it means we'd need more exotic methods. For instance, importing volatiles, crash comets full of ammonia or water into Mars, or use super powerful factories to create synthetic greenhouse gases. These ideas involve titanic scales of energy and time. Smashing a few hundred comets into Mars might deliver enough gas and water, but guiding comets safely is science fiction. Level for now. Manufacturing an atmosphere would require literally covering Mars in factories running for perhaps centuries, outputting gas. Assuming we somehow succeed in raising the pressure to something like half an Earth atmosphere and temperature to near 0 degrees average, we'd then consider biosphere introduction. Initially, we'd have a mostly CO2 atmosphere. Humans still couldn't breathe that. It's for plants and microbes. We might sow the planet with hardy pioneer life, genetically engineered algae or lichens that can tolerate cold and high UV to start producing oxygen and creating soil. Over long spans, these could build up O2. Earth took billions of years and specific conditions to get an oxygen-rich air, so expecting a quick oxygenation is unrealistic. It might take millennia or require further intervention. Another approach to terraforming is more localized, paraterraforming. Instead of trying to change the whole planet at once, build large enclosed regions, e.g. giant domes or even crater, wide transparent canopies, and terraform inside them. This is more achievable near term. You could seal off a large crater with a strong clear roof, then pump air inside, seed water and life there. That crater would become a shirt-sleeve valley, perhaps tens of kilometers across, where earth plants grow in Martian soil under a controlled climate. It's like creating big oasis patches on Mars. Over time, you enlarge these patches. This is not full terraforming, but could make sizable areas habitable relatively sooner. The ethical side. If Mars harbors any native life, do we have the right to alter the planet and potentially destroy that biosphere? This is a serious concern. Planetary protection protocols currently forbid intentional contamination of Mars until we're sure no native life exists, or until we decide to override that. Many argue we should thoroughly search for Martian life first. If Mars is sterile, terraforming is a grand extension of life. But if Mars has even a simple biosphere, terraforming might obliterate it, which some would view as unethical and hubristic, ending an alien ecosystem for our own ends. Possibly a compromise, if Martian life exists, maybe confine terraforming to regions without it, or even attempt to include Martian life in the terraformed environment. Beyond Mars, people talk about terraforming Venus, cooling it down, removing its thick CO2 atmosphere, but that is an even more Herculean task. Or terraforming moons like Titan. Some speculative future tech, like redirecting asteroids or even altering orbits, enters these discussions. For instance, one wild idea: send large mirrors or lenses to focus extra sunlight on Mars to heat it, essentially an artificial greenhouse effect via orbiting mirrors. Conversely, for Venus, put a giant shade at Sun, Venus-Lagrange point to cool it, and then perhaps bombard it with hydrogen to lock up CO2 into rocks. Colossal geoengineering beyond current reach. Time is a factor. Terraforming is slow. Even optimistic scenarios see centuries to thousands of years to get a breathable Mars atmosphere. That's a timeline that dwarfs human political cycles and maybe attention spans. It raises practical questions. Who begins a project that none of their great-great-grandchildren will live to see completed? It requires a civilization committed long-term, or an automated process that runs without much oversight. A possible path is that once we have colonies, they might incrementally terraform for their own expansion, not a formal global terraforming plan, but by making larger safe zones over time, they in effect terraform bits of Mars which eventually merge. One might also ask, should we terraform at all? Some argue leaving Mars as is, a natural reserve or science lab, is better, and humans can adapt to Mars via technology rather than adapting Mars to humans. Others feel giving Mars a biosphere would be giving it life and purpose, a grand altruistic act to spread Earth's richness. In fiction and futurology, a fully terraformed Mars is depicted with flowing rivers, blue patches of sea in its northern basin, forests in valleys, essentially a second Earth with rust-colored rocks and maybe pink skies. Perhaps most appealingly, it's a future where humans can stand on another world and breathe freely, having literally reshaped a planet to suit life's needs. This is an ultimate expression of life becoming a force of nature beyond Earth. Even if we conclude classical terraforming is currently beyond reach, the pursuit of it teaches valuable lessons about planetary climates, even Earth's. Already, studying how to warm Mars sheds light on our warming Earth. The magnitude of Mars's CO2 deficit relative to needs also humbles us. It shows how special Earth is to have the right air, and how difficult it is to replicate that elsewhere. Terraforming talk leads to philosophical perspective. It's playing creator on a planetary scale, something far beyond any collective endeavor we've done. It requires both incredible technology and nearly spiritual will, a devotion to making a dead world living. Time, patience, vastness, these become tangible factors, tying into the earlier theme of slowness and patience in space travel. Perhaps terraforming, if it ever happens, will be done by our distant descendants with powers we can't yet wield. Or perhaps we'll choose gentler terraforming, sustaining bubbles of life in hostile places and gradually enlarging those. Either path, the notion that we might reshape worlds is a testament to the human blend of audacity and creativity. It pushes the boundary of home beyond Earth, not by adapting ourselves to every environment, but by also adapting environments to us. It's a form of cosmic gardening, with planets as the canvas. In the far future, if we overcame the obstacles and Mars stands verdant, what a legacy that would be. Imagine travelers from Earth arriving on a terraformed Mars centuries hence. To them, it's a vibrant world. They might not fully appreciate that once it was barren, and it was human effort that greened those plains. But perhaps plaques or monuments would dot the Martian parks. In memory of the terraformation, begun 2250 AD, completed 2700 AD by the peoples of Earth and Mars. The ethical debates would be settled by history. Martian life would now be abundant, though imported. Earth trees, Martian, evolved descendants of Earth microbes, maybe even animals if they were eventually introduced in controlled refuges. It would be a second cradle of Earth life. It would be a second cradle of Earth life on a once barren world. A living monument to human creativity and persistence. The red deserts would have blooms of green, and a future traveler might forget that Mars was ever uninhabitable. The story of that transformation would be told in school books, how humans became, in effect, the gardeners of planets. Yet we must temper this vision with humility. Terraforming is no simple panacea. It's an extreme undertaking that could span millennia and demands wisdom. As one study concluded, there is not enough CO2 remaining on Mars to provide significant greenhouse warming with known methods. In other words, we can't just push a button and give Mars a breathable sky. The raw materials aren't readily there. This reality, Czech teaches us to cherish Earth's perfectly tuned environment even more. Our planet is a rare jewel, all the ingredients for life in just the right balance. In attempting to emulate that elsewhere, we appreciate how complex and precious a biosphere is. Perhaps the greatest lesson of the terraforming dream is the reinforcement of environmental stewardship at home. If we ponder greening Mars and see how hard it is, it may motivate us never to let Earth go barren by our own folly. In the end, whether or not humanity ever fully terraforms a planet, the act of trying, even on smaller scales, will mean we have grown into a role of cosmic custodians. We will have moved from simply living off the land to literally reshaping worlds to support life. That is a profound responsibility. It forces us to decide what values to carry into the cosmos. Do we preserve alien nature as we find it, or do we spread the life we know? There is no easy answer. Perhaps the answer will differ case by case. Mars might become New Earth, while another world we might leave untouched as a scientific preserve. Our descendants might look back at these early debates as the first ethical steps toward becoming a multi-world species. For now, terraforming remains a distant aspiration. But in laboratories and computer models, we tinker with the ideas, learning how atmospheres work, how greenhouse gases warm or cool. This knowledge loops back to help us manage Earth's climate. In a sense, by dreaming of terraforming Mars, we are also discovering how to re-terraform Earth if needed, to undo some of the damage we've done with climate change or ecological destruction. Learning to shape a harsh planet into a livable one might teach us how to keep a livable planet from becoming harsh. Terraforming thus embodies both our ambition and caution. It is the ultimate expression of letting imagination orbit physics, as we attempt to make imagination into physics, turning what is into what could be. Whether it takes 300 years or 30,000, the thought that one day a distant world could be alive with Earth, descended forests and oceans is a powerful beacon of hope. It suggests that life is not chained to its cradle, but can spread and blossom anew in the cosmos. In that sense, successful terraforming would be like life itself, planting seeds in new soil, carrying forward the legacy of our home into the wider universe. Artificial ecologies, gardens in orbit, and biophilic design. Across all these ventures, stations, bases, ships, and new worlds, one thread is vital. We need nature with us. Humans evolved among rustling leaves, flowing water, and other living creatures. Our minds and bodies crave those cues. The sterile metal walls of a spacecraft, however advanced, can never fully satisfy the longing for green growing life. Thus, wherever we go, we bring pieces of Earth's ecology and attempt to weave them into our habitats. From a small potted plant floating in a space station window to entire biodomes on Mars, biophilic design will be key to making space homes feel like home. We have already seen the impact of tiny gardens in orbit. The ISS crews have tended little patches of zinnia flowers and lettuce in microgravity as part of experiments, and they report how seeing a bit of green and orange bloom amidst the machinery lifted their spirits tremendously. They also very much like growing plants. It boosts morale and provides fresh oxygen and smell, notes one Canadian Space Agency article. Indeed, astronauts have said the scent of fresh flowers or herbs in that recycled air environment was almost magical. These are artificial ecologies in miniature: a small rooting pillow of soil, LED lamps replicating sunlight, water delivered carefully so it doesn't float away, a whole life system engineered into a box. And yet, the result is real: a living organism sharing the habitat, responding to the care of the crew. It's a preview of what larger green spaces could do. In future orbital stations or lunar Martian bases, designers are already planning dedicated green modules or plant walls inside habitats. A hydroponic wall of climbing plants or a central atrium with a few trees under an LED skylight could drastically change the ambience of a confined base. Instead of purely synthetic environment, one would wake to the humid freshness of leaves transpiring moisture, maybe even birdsong. Biophilic design has proven benefits. reduced stress, improved mental well-being, even better cognitive performance. In a Mars base, a greenhouse might double as both food source and psychological refuge. Colonists might go there off duty to sit among the plants and feel a semblance of Earth. One can imagine a Martian park in a pressurized dome, complete with a little pond and a bench by it, where one can go meditate under the light of a simulated sunset. These artificial ecologies aren't just decoration, they become functional parts of the life support loop. Plants regenerating oxygen and consuming CO2, maybe providing some food. In essence, we create a self-sustaining garden within the technology, each supporting the other. Engineers consider things like which plants are best: sturdy, low, light-tolerant, high oxygen output, or edible. Possibly future habitats will favor multi-purpose plants. There's even talk of genetically engineering plants specifically for space. Maybe a super algae that is extra efficient at scrubbing air, or dwarf wheat with higher yields. But beyond utility, we'll also include plants just for beauty and comfort. A rosebush on Mars might not feed anyone, but the first Martian, born teenager, might gift a rose grown in Martian soil to their sweetheart, a gesture that ties human emotion to this new world's nature. Biophilic design goes beyond plants. It means using natural materials and forms so inhabitants feel less machine, encased. Windows to space count too. Seeing the Earth, moon, or stars can instill awe. But overall, opening views, curving shapes reminiscent of natural forms, and warm natural colors can make a station more psychologically livable. Future architects might model habitats after seashell spirals or cellular lattices, shapes our brains find inherently organic. This is already an earthly trend in architecture. Expect it to be even more valued off-world. There's also the concept of creating closed ecosystems for research and pleasure, like a small pond ecosystem in a bubble, where fish, plants, and microbes form a cycle. On Earth, experiments like Biosphere 2 tried to enclose ecosystems. They hit difficulties, but in smaller scales and with continuous management, they can work. An orbital station could have an aquarium tank with fish, not just for decor, perhaps also for protein food source. Astronauts have expressed joy even from simple life, like watching brine shrimp or insects they brought along. The movement of other living creatures breaks monotony of human-only company. Artificial ecologies also teach us about sustainability. If we learn to keep a little garden alive in space with limited inputs, we learn how to be efficient and balanced. Lessons directly transferable to Earth farming and vice versa. The plants grown in microgravity have shown us how life responds to conditions utterly different. This knowledge expands our understanding of biology. How adaptable is life? We see that with a bit of help, it can survive even off Earth. There's a poetry, too, in carrying seeds across space. Consider a scenario. On a generation starship, an elder might pass a precious heirloom seed to a grandchild. This is a cutting of the oak from our ancestral home. Plant it when we reach the new world. That act symbolizes continuity of life's thread. Indeed, if we eventually spread to distant exoplanets, we will likely bring with us a Noah's Ark of biodiversity, seeds, spores, embryos, an artificial selection of Earth's ecology to sow elsewhere. We become, literally, gardeners of the galaxy, curators of Terran life in foreign soils. Even on near-term missions, the presence of life is grounding. Many ISS astronauts have commented that caring for the little space garden gave them a sense of normalcy and responsibility beyond mission tasks. Watering a plant or pollinating it by hand became a cherished routine. It's a reminder that no matter how advanced our machines, we remain biological beings who need other life around. Biophilia in design might also mean ensuring crew have exposure to the natural cycles. Artificial day, night lighting, to mimic Earth's diurnal rhythm, helps sleep and mood. Already the ISS installed an advanced LED system that shifts color temperature to assist astronauts' circadian rhythms. Future habitats could simulate seasons gently, or at least allow personalization. The point is to not have an unrelenting, featureless environment. Variation, color, the sound of a small indoor fountain gurgling recycled water. These little touches of nature can make a tin can into a home. One can imagine on a lunar base, after a long EVA, an astronaut comes into the habitat, takes off their helmet, and immediately smells something cooking with basil from the greenhouse. They float to the plant rack, pluck a fresh basil leaf, and inhale its aroma. Suddenly, the moon feels not so alien. Or on an orbit station, a tired engineer before bed drifts into the Zen corner, where a small bonsai tree grows under a lamp and just watches its tiny leaves for a while, finding calm. These are small mercies, but vital ones. They remind us why we're bringing humanity to space, not just our bodies. Humanity includes our affinity for life and beauty. As settlements grow, artificial ecologies won't be so artificial. They'll become true ecologies, interlinked with our presence. A Mars city in 500 years may have outdoor parks under a vast dome, where evolved Martian varieties of Earth plants create a unique but lush landscape. There might be Martian songbirds, descendants of Earth finches, but maybe adapted to lower gravity with broader wings. The colonists might find the most profound satisfaction in these parks. After working in regolith mines or labs, they relax under an alien sycamore tree, listening to Martian wind rustle its leaves. At that moment, the line between Earth and Mars blurs. Life has unified them. The ecological cycles begun in little orbital plant chambers will have scaled up to forests under an alien sky. Bringing gardens with us is not mere luxury. It could be what ensures we remain psychologically whole. As the proverb goes, you can take the human out of Earth, but you can't take Earth out of the human. Our future habitats must carry a spark of Earth's nature inside them. In doing so, we create continuity. Imagine centuries from now, a child on a far-off world touches a rose petal and knows its ancestors came from a blue planet, unimaginably distant. Yet through that living petal, they are connected. These living connections will be our emotional umbilical cord across the void. So, as we extend our reach outward, we will always try to pack a garden. Even if it's a garden of microbes recycling our air, or a single vine creeping along a station wall, it is life traveling with life. The artificial worlds we build, ships and stations, need not be sterile constructs. With thoughtful design, they can become vibrant microcosms. Space habitats might buzz softly with hydroponic bees pollinating tomato flowers, or glow with the bioluminescence of engineered algae lighting a hallway at night. There's creativity in how we integrate life into technology. In sum, our species' success off-world will owe a lot to the humble green leaf and the wisdom to incorporate nature's design. As we plant gardens in orbit and beyond, we carry forward the best of Earth, its living heart. In turn, those plants and natural elements will sustain our hearts and minds, ensuring that even in the starkest emptiness of space, we are never truly alone. We will live surrounded by echoes of home, and in nurturing those echoes, watering our cosmic gardens, we nurture ourselves. Culture in space, music, art, relationships, belief. When humans leave Earth, they do not just carry biology with them, they carry culture, the rich tapestry of music, art, stories, religion, and social customs that define us. Space is often portrayed as high, tech, and utilitarian, but wherever people go, they bring their humanity in full. Already on the International Space Station, astronauts have played musical instruments, painted watercolor art, celebrated holidays, and even quietly prayed or performed religious rituals in microgravity. These acts of culture are not incidental. They are profoundly important for emotional well-being and identity. As we build new societies off Earth, those societies will develop their own unique cultures, blending Earth traditions with novel experiences of space. The mind in space not only needs connection to nature, but also connection to heritage and creative expression. Consider music. In 1965, astronaut Walter Schirra brought a harmonica to Gemini 6 and playfully performed Jingle Bells, the first song from space. Since then, guitars, keyboards, even bagpipes have flown to orbit. On the ISS, Canadian astronaut Chris Hadfield famously played guitar and recorded a rendition of David Bowie's Space Oddity floating in the cupola. It moved millions on Earth because it combined human art with the cosmic setting. The crew often sing together or listen to their favorite songs to relax. Music in space continues the age-old practice of using art to cope with isolation and bond communities. In a Mars base, one can easily imagine evenings where the crew gathers in the habitat module after dinner and someone strums a guitar. The familiar chords and lyrics might evoke memories of Earth, bringing cathartic tears and also joy. Over time, they may write new songs, perhaps about the Martian landscape, or a humorous ditty about the quirks of low-gravity life. These become the folk songs of that community. Art will likewise flourish in unexpected ways. Astronauts already take stunning photographs of Earth, arguably a collaborative art between human and orbital vantage. Some have sketched or painted. NASA's Nicole Stott painted a watercolor of Earth in orbit. Her painting is gentle and blue, capturing the essence of her view. In the future, Martian colonists might turn local materials into art. Imagine pottery made from Martian clay, glazed with chemicals giving it a distinct rust, red sheen, etched with scenes of moons Phobos and Deimos in the sky, or sculptures crafted out of metal from old spacecraft parts, giving new aesthetic life to engineering scrap. Visual artists will find endless inspiration. The soft peach of the Martian sunset, the jagged shadows in the moon's eternal sunlight near its poles, the swirling clouds of Jupiter if one lives on a station near the giant planet. Relationships in space will evolve too. Thus far, professional crews have mostly kept a strict work, like camaraderie, but as civilians and families venture out, love and friendship in the cosmos become part of the story. There may one day be marriages on Mars, children born under its pink sky. How will human romance adapt when one can't go out for a stroll in the park without a pressure suit? Perhaps date nights happen in the base's greenhouse amid the flowers, or couples reserve a VR session to simulate a beach vacation on Earth for an hour. The constraints might make relationships more intense in some ways. You rely on a small group for all social needs, yet also more deliberate. Each person is precious, and one cannot easily find new company if things sour, so colonists might develop strong conflict resolution skills in personal relationships. We may also see new social customs. For example, perhaps on a long voyage, the ship's community invents a holiday commemorating Halfway Day, when they've traversed half the distance to their new star, a day of music and thanks. Or on the moon base, they create a tradition that every Apollo landing site's anniversary is celebrated by reading out loud the words of the first moonwalkers, bridging past and present. On Mars, the arrival day of the first colonists might become the colony's founding day, marked by games and a feast of the first harvest from their greenhouses. Belief systems also travel with us. Already, astronauts of various faiths have found ways to observe their practices in orbit. There has been communion taken on the moon. Muslim astronauts have faced Mecca in orbit and timed prayers according to a workable schedule of the 16 sunrises a day. Jewish astronauts have brought menorahs or said Shabbat prayers in space. These personal beliefs provide strength and continuity. In new settlements, religion may take on modified form. For instance, if you want to hold a multi-faith service on Mars, you might incorporate the awe of the new planet into it, thanking the Creator for both Earth and Mars. Martian-born people may found entirely new spiritual philosophies, perhaps centered on the idea of being Planet B of humanity, stewards of a second chance, which could infuse an almost spiritual mission to their society. Anthropologists speculate about astro-religion, how the overview effect might seed new faith, like reverence for the universe itself. Many astronauts indeed describe their space experience in spiritual terms, even if secular, a feeling of interconnectedness and transcendence. This could crystallize into organized expressions on a colony. One could imagine Martian settlers gathering at every opposition for a kind of Martian Thanksgiving, spiritually giving thanks for the journey and asking for continued guidance. Identity and culture are deeply linked. Over generations, space communities will form identities distinct from Earth nations. A Martian culture might emphasize self, reliance, innovation, and the frontier spirit in songs and literature. They might develop their own slang, some already emerging among astronauts. Future slang might include terms like sojourn or to space it. These linguistic quirks become badges of belonging. Eventually, entire art forms may evolve unique to space. Perhaps Zero, gravity dance, becomes a celebrated performance art, with dancers gliding in 3D accompanied by ethereal music, something impossible on Earth, giving space colonies their own art genre. Or orbit cinema, films made in space, using real weightlessness as their medium. We've already seen the first hints. Short films and many documentaries have been filmed by astronauts. Future storytellers born in space will no doubt use their environment as a canvas for creativity. As culture flourishes off-world, it will also serve as a bridge home. When a Mars poet writes a moving poem about seeing Earth rise, that poem travels via radio waves back to Earth, and people here gain a new perspective through Martian eyes. Culture becomes a two-way conversation across space. Earth culture feeds space settlers, and space culture feeds back fresh ideas and inspiration to Earth. The loneliness of vast distance can be mitigated by sharing art and celebrations. Already, there have been live concerts linking ISS and Earth, joint educational events, even art exhibits where astronauts draw, and those drawings are shown on Earth. In the future, we might have a solar system cultural festival, with contributions from Moon, Mars, orbital stations. Everyone tuning in via communications to share dances, songs, and art across the void. It could be as significant as the Olympics, a way to unite far-flung branches of humanity in common creative endeavor. In summary, as we settle beyond Earth, we do not shed our humanity. We carry it with us in full color. The need to create, to celebrate, to love and believe. These persist in metal cans orbiting high, or habitats buried in regolith. In fact, in the starkness of space, these cultural elements become even more crucial, like the psychological oxygen that keeps our souls alive. We will see Christmas trees gently floating in spacecraft, Ramadan fasts observed on Mars with creative timing of sunrise, sunset, new festivals like low-G games on the Moon, where kids play novel sports. We'll see weddings under a Martian dome, with guests throwing confetti that falls ever so slowly in the lighter gravity, a beautiful sight. We'll hear lullabies sung to children on a generation ship as the stars drift outside, perhaps old Earth folk songs repurposed for star voyages. Human culture has always adapted to new frontiers. Think of how American frontier life gave rise to country, Western music, or how Polynesian seafarers developed rich navigational myths. Space is the next frontier, and it will be no different. Our descendants out there will tell myths about their first explorers, draw inspiration from their new skies, and add new chapters to the human story. One day, a child on an exoplanet might learn in history class about Armstrong and Gagarin as legendary figures, and also celebrate Farmer Nguyen, who devised the irrigation system that allowed their colony to thrive, local heroes adding to the pantheon of culture. Ultimately, culture in space ensures that as we physically adapt to new environments, we also psychologically and socially adapt. It knits people together, gives comfort, and infuses life with meaning beyond mere survival tasks. It is how an outpost becomes a community, and how a collection of explorers becomes a people. Without culture, a colony would be a cold camp of temporary sojourners. With culture, it can blossom into a new branch of human civilization with its own identity and pride. In carrying songs, art, and faith to the stars, we carry the true essence of humanity, proving that wherever we go, we remain creatively and spiritually human. Children in space. Development without Earth. In a small habitat on Mars, a newborn cries for the first time, the first human voice to be born on another planet. This moment, still in our future, will mark an extraordinary milestone: human childhood beyond Earth. What will it be like to grow up in space or on another world? This question is both scientific and deeply emotional. Children represent the continuation of our presence. When the first child takes their first steps under a lower gravity, or draws their first crayon picture of a landscape with 2 moons in the sky, we will witness the dawn of a truly multi-generational off-world society. From a biological standpoint, we have many unknowns. No child has yet been conceived, gestated, and born off Earth. The effects of low gravity on fetal development are uncertain. On Earth, gravity cues help shape the vestibular system in utero. In microgravity, or even Mars, 0.3 Hg, will a developing inner ear form differently? It might. We may find that babies born in low gravity have a different sense of balance and strength. Bone development could be affected. Without full Earth weight, bones might grow less dense or in a slightly different architecture. We might counteract that with rotating habitats. But these are untested interventions. When it comes to birth, microgravity could actually ease labor in some ways. But controlling the environment is tricky. On Mars, 0.38 G, it might be easier for a mother to support herself in any position comfortable. Medical teams will have to adapt techniques and equipment. It's likely that until much research is done, any off-world birth would be considered high risk and have contingency plans to get the mother to Earth if needed. Over time, as we gain confidence, births on Moon Mars might become routine, but in early days they may be rare and carefully overseen. Imagine being a child on a generation ship or Mars colony. Their childhood environment is dramatically different. Maybe a few habitat modules, some pressurized tunnels, a very limited physical world compared to Earth's wide, open spaces. Their playground is perhaps a big cylindrical room where they can bounce off walls. How to ensure healthy social and motor development? Colonists would likely emphasize creative play in novel ways. For instance, games that use low gravity. A kid can jump 5 times higher on Mars, which might be thrilling, and promote athletic skill, albeit different ones than Earth kids. Martian kids might become superb jumpers and climbers of indoor rock walls because their weight is light. However, things like learning to ride a bike or throw a ball with Earth, like trajectory, won't be the same. They might ride modified bikes built for lower gravity and pressure suits if outside. Outside, that's a concept for off-world kids that isn't the same as Earth's outdoors. On Mars, outside requires a suit, a helmet, and parental supervision akin to a deep sea dive. It's not the carefree running in a field. Perhaps Martian children will have safe playground domes, small transparent bubbles connected to the habitat where they can play outside in a shirt-sleeve environment with natural sunlight filtering in, effectively a park under glass. They'd see the rusty landscape around, but still be in breathable air. I suspect colonists would prioritize building such recreational spaces, especially for kids, even if small, to give them some psychological sense of space and connection to their planet beyond metal walls. Education will also adapt. Children in space would learn not only Earth history and science, but also their local environment intimately. Even a toddler on Mars will know that air comes from the machines and plants, not to waste water because it's all recycled. They will grow up inherently with a sustainability mindset and a comfort with technology that keeps them alive. A child might casually talk about CO2 levels or radiation alerts as things to be mindful of, stuff Earth kids rarely consider. This could make them mature in certain respects earlier, carrying responsibilities. That responsibility might imbue them with a certain seriousness or collective spirit. There's also the cultural identity aspect. A child born on Mars is a Martian from day one. If there are a handful of them, they become a special group, the first native generation. Adults might treat them with both tenderness and perhaps awe. These kids are truly the pioneers of a new society. Over time, as more are born, that mystique will normalize. But still, these children will form the first peer group off Earth. They might develop an accent or dialect distinct from Earth languages if isolated enough. We saw in isolated Earth communities that within a few generations, local dialect and folklore appear. Martian nursery rhymes may differ from Earth's.
Physically, how might kids differ? If raised in 0.38 g, they may grow taller. Their muscles, never having to push against full 1 g, might be leaner. This could become a health issue if they travel to Earth. Likely a Martian, born person, might find Earth gravity extremely taxing. It raises ethical questions. Are we creating humans who can't ever safely visit Earth due to their adaptation? Some scientists suggest we might want to ensure children spin in a centrifuge regularly to approximate Earth gravity time to mitigate such differences. If not, a true Martian might need lengthy training to handle Earth gravity or even exoskeleton assistive suits to move on Earth. Conversely, Earth-born children migrating to Mars might revel in suddenly being able to jump higher and carry heavy objects easily, but their bodies might change over years to a new equilibrium.
Psychologically, children are adaptable. A child born on a spacecraft might take 0 μg for granted and be a natural at maneuvering. We might see kids making a game of 3D tag in the station corridors, utterly at home in microgravity. Perhaps healthier in that environment than adults, because their neuroplasticity is high. However, could living without Earth's normal cues cause developmental issues? One concern: vision. On Earth, distance vision develops as kids see far off horizons. On a spacecraft, the farthest internal line of sight might be 20 meters in a module. Would children become nearsighted due to lack of distance viewing? Possibly. Already many ISS astronauts get a bit of blurred vision from fluid shifts and lack of far focus. We might need to provide some way for kids to focus far, maybe virtual reality sessions simulating looking across a vast field to exercise their eyes. The social circle for children in a small colony will be tiny, maybe only a handful of other kids and the few dozen adults. This is akin to growing up in a very small village or research station. They might be old souls, interacting mostly with adults and maturing quickly in speech and knowledge. But they might also yearn for more friends. The colony might eventually have to schedule playdate by radio, video communications with kids on Earth or the Moon to give them a broader social exposure. Imagine a Martian 5-year-old having a weekly video play session with a cousin on Earth, each showing their toys and environment. This could keep them feeling connected to humanity at large. Moral and philosophical perspectives will also shape how we treat space. Born children. They did not choose to be in a risky environment. Their parents or society did. So there's a duty to maximize their opportunities and safety, maybe more so than even on Earth, because they are more vulnerable. Likely, colonists would be extremely protective and rigorous in planning for kids, e.g., ensuring radiation shielding is enhanced in habitats because children's tissues are more sensitive to radiation's long-term effects. We might design special small suits or escape pods specifically for rescuing children in emergencies. On the flip side, children will bring lightness and normalcy to space communities. Their laughter, their growth milestones, will remind everyone why building a future in space is worthwhile. It's not just exploration, it's building new homes for the next generation. The first toddler to scribble a drawing of Mars's twin moons in the sky might hang it on the habitat wall, and that likely brings tears of joy to hardened engineers' eyes. A child asking, "Why is Earth so bright in the sky?" will spark impromptu lessons at the dinner table, bonding everyone in wonder through a child's eyes. Generational continuity is the ultimate test of an off-world settlement success. The day a baby takes breath in a Mars habitat and survives to grow is the day that colony is no longer just an outpost, but a nascent civilization. Each birthday of that child will be a cause for colony-wide celebration. We kept them safe and thriving another year on Mars. They are the living proof that human life can propagate away from the cradle. In later years, when that child becomes an adult Martian who perhaps has never been to Earth, they may feel Earth as almost a mythic place, pictures and stories passed down. They might ask their parents or grandparents what rain felt like, or what running under an open sky was, and those elders will recount these things like legends. On Earth, rain falls from clouds in the sky, water from above, and there are great forests where you can walk for days. The young Martian might listen wide-eyed but not fully grasp it, just as today we listen to descriptions of places we've never been. And maybe they will dream, one day, of visiting Earth, the same way an Earthling dreams of visiting Mars. By then, technology might allow safer travel back and forth, and perhaps some Martians will journey to Earth as reverse explorers, marveling at the deep blue sky, the weight of full gravity pressing their shoulders, the bizarre experience of an ocean's waves. In that meeting of Martian, born and Earth, born, we'll truly see how children of space have become a new branch of the human family, different in experience, but human through and through, bridging worlds with shared curiosity. Thus, the story of children in space is one of adaptation and hope. They are the ultimate payload of all our rockets, the seed of future generations sown on distant ground. Ensuring their health and happiness will drive innovation. Their presence will soften the environment. You can't keep a colony too Spartan when children need play and color. You'll have to include playful design, decorations, festivals for them. In turn, they give the colony a future to strive for. As one Mars settler might say, watching their child sleep, "We came here to make a new world for them." And if that child one day sings a Martian lullaby to their own child, under a terraformed sky perhaps, then humanity will have truly taken root beyond Earth. And, society. Beyond Earth, politics, economics, and identity. As human outposts grow into settlements, they will inevitably develop the structures of society, our systems of governance, our economic exchanges, and our sense of collective identity. Beyond Earth, these will evolve under unique pressures, vast distances from terrestrial authority, reliance on self, sufficiency, and mingling of people from different Earth cultures in tight quarters. The result may be new social paradigms or insightful twists on old ones. How will we govern a Mars colony? What currency or trade will drive a lunar economy? Will those born on different worlds see themselves as one people or many? Such questions move us from the realm of engineering life support to engineering society, a challenge as profound as any rocket science. In the early phases, a space settlement likely operates under the mandate of Earth nations or agencies that founded it. For instance, a Mars research base might initially be run by a coalition. The crew follows a charter agreed upon on Earth, but as the base becomes a permanent colony with hundreds of residents, Earth-based micromanagement becomes impractical. Political power will begin to shift towards the colony itself. We can foresee Martian settlers forming a local council or assembly to handle day-to-day decisions, essentially a form of
Government. Initially, Earth authorities will guide broad policy, but over years, the Martians will push for more autonomy, especially if they become economically self-sustaining. This mirrors how terrestrial colonies in history gradually demanded self-governance. The difference is distance. Earth can't easily send troops or impose direct control if Mars decides something divergent. So any governance likely has to be built on cooperation and mutual interest rather than force. We might witness the birth of the first space nation. Perhaps at some point, Mars declares itself an independent polity, not necessarily in conflict with Earth, but as a logical step as their population grows. There is precedent in treaties like the Outer Space Treaty that forbids national appropriation of celestial bodies, which implies no Earth nation can own Mars. So any settlement might form a new, local nation or a corporate entity turned quasi-government if established by a private company. The legal frameworks are untested. It could be peaceful. Earth governments might even recognize a Martian republic or commonwealth as a self-governing entity within some loose association. Laws and justice in such a society will have to adapt to extreme environments. Crimes like sabotage of life support would be heinous in space. Property ownership may be communal at first, transitioning to more private property as abundance increases. A small colony might operate much like a ship with a commander's law. A larger one might draft a constitution. Could Martian settlers have representation in Earth governments, or will they have their separate legislature? These are fascinating possibilities. On the economic front, early colonies rely on Earth's funding and supplies, a command economy out of necessity. As they become productive, an internal economy forms. We might see a barter system initially if no formal currency is introduced. Eventually, likely a local currency or credits tied to Earth currency will be used. Perhaps Martian credits that are exchangeable with Earth dollars via some treaty or company backing. Off-world economies could at first be small closed loops. Everyone in the base works essentially for the maintenance of the base. Any profit is survival and maybe stockpiling resources. But as they produce surplus, trade begins. A Mars colony might export valuable minerals or scientific data to Earth in exchange for luxury goods or specialized tech they can't produce. Interplanetary trade could develop, e.g., Mars sends platinum, group metals to Earth. Earth sends manufactured electronics and medicines to Mars. If lunar settlements mine helium, they might trade that with Earth's future fusion power plants for goods or simply for currency to buy things. Economies in space will also have to deal with labor and automation. Likely a high degree of automation in hazardous environs, but human oversight still crucial. Everyone in a colony might have to wear multiple hats. Over time, actual professions will diversify. Someone might make a living purely as a teacher or artist in the colony, once it's big enough to support non-engineering roles through trade or internal economy. Imagine a Mars colony of 500. They might have 1 or 2 dedicated teachers, a doctor, some technicians, some miners, etc. There might also be the seeds of a Martian market, perhaps a weekly bazaar where people exchange homemade goods. Out of such simple exchanges, a more formal economy can emerge. What about identity? Over a few generations, Martians or Lunarians will likely identify more with their planet or habitat than with Earth nations of their ancestry. A person might say, "I'm a Martian of Arsia Mons settlement," rather than, "I'm American" or "I'm Chinese," if the colony culture has blended nationalities. In fact, space colonies might be melting pots by necessity, a small community with diverse origins forging a new unified culture. Early ISS crews, and now the Gateway, likely use an official lingua franca, but local dialect might incorporate words from Russian, Chinese, Arabic, etc., as multi-ethnic crews settle permanently and raise kids. Kids might mix phrases from their parents' tongues, or coin new ones from mishearings. Thus the Martian Creole might be born. flags and symbols of off-world societies will come. Perhaps the Mars settlement designs a flag featuring Mars's moons or a silhouette of Olympus Mons. Those symbols become rallying points. Anthem songs might be composed. All the elements of nationhood could form in microcosm. One interesting aspect: distance equals independence. With Earth 15 minutes to 20 minutes of light, speed time away in communication, Martian society will operate much on its own rhythm. Their news cycles will differ. They'll make decisions and inform Earth later. This fosters a psychological sense of separation. When Earth and Mars are on opposite sides of the Sun, even comms can be disrupted or heavily delayed. During those periods, the Martian colony truly experiences what it is to be a world apart, needing to solve any crisis alone. This can strengthen local solidarity and reduce psychological dependency on Earth directives. In orbital colonies closer to Earth, the independence is less forced by distance, but they may still form unique governance. Perhaps such a station is corporate, owned and run somewhat autocratically initially, but if families and multiple generations live there, they may push for a more democratic community-run system akin to a city-state in orbit. We have to consider conflict and law externally too. Could space societies conflict with Earth or each other? If Mars declares independence and Earth attempts to insist on control, a conflict could arise. Though outright, war is unlikely given distances and costs. More probable are negotiations resulting in a status somewhat like how colonies became dominions or commonwealths historically. But we might see disputes over resources. Therefore, early on, humanity will need to extend international law into space domains, updating treaties to address colony rights, resource rights, and conflict resolution beyond Earth. Possibly new institutions, like a solar council, will form to give representation to off-world communities in global decisions. Economically, if off-world production becomes significant, those off-worlders will have leverage and stake in Earth's economy, further entangling interests. A Martian polity might own companies on Earth, or vice versa. There might be something akin to colonial mercantilism, hopefully more enlightened, where Earth and Mars find mutual benefit and share profits, rather than one exploiting the other. The mistakes of colonial history on Earth could be avoided by mindful legal agreements up front. Over time, each off-world society will answer the question, who are we? The first-generation Martians, many being emigrants, will have split identity, but their children and grandchildren might see Earth as the old world. They might even form gentle prejudices like, Earthers are weak in bone, but strong in bureaucracy, or Earth folks might stereotype Martians as reckless and independent. Over generations, these identities become as distinct as nationalities today. Perhaps new ethnicities even, if some biological divergence occurs. If terraforming advances and generations live and die on Mars, after many centuries, they truly become Martian humanity, a branch that would see Mars as the normal environment and Earth as exotic. Visits between planets could then be akin to ancient state visits between faraway countries, requiring adaptation, but reinforcing that we are still one human family across planets. Cultural exchange will serve to maintain a bit of unity. Maybe Martians still celebrate some Earth holidays. Meanwhile, Earth might adopt new holidays honoring space achievements or in solidarity with space communities. In essence, expanding into Space Force's humanity to confront its identity on a larger scale. Historically, we expanded across the globe and formed myriad identities. Now, as we spread to other worlds, will we fragment further or find a higher unity? Possibly both. Local societies form, each with autonomy and pride, but all perhaps see themselves collectively as spacefarers or extraterrestrials in the literal sense. And relative to any hypothetical alien intelligences, all those differences shrink, and we'd present as just humans together from different planets. Politics might thus evolve multi-layered. local governance for each colony, and an overarching interplanetary council to manage relations and common issues. Imagine a future UN with not just nation, state representatives, but also planetary representatives. An ambassador of Mars, a delegate from the free moon settlements, an envoy of Titan colony. In a science fiction-like scenario, these bodies debate joint missions or settle disputes. This could be centuries away, or maybe sooner if we get multiple off-world outposts by late 21st century that warrant such coordination. We might also see experimentations with social systems. A small Mars town could try a more direct democracy via technology, or an orbital habitat might be run by a cooperative where each member has equal share and say, essentially a floating kibbutz. Freed somewhat from Earth's entrenched institutions, these pioneering communities might innovate with social contracts, guided by necessity. However, human nature being what it is, power structures and conflicts of interest will inevitably arise. Perhaps some will hoard rare items from Earth or monopolize certain knowledge. Jealousy and politics will then brew. Recognizing this, early charters will likely emphasize fairness and preventing destructive competition. It's often noted by crew that in space, cooperation is not just idealistic, it's literally survival. One person's sabotage or selfishness could kill everyone. So social norms in space are strongly oriented toward teamwork and self-restraint. This ethic might persist into later generations as a cultural value. Martians might consider Earth folk too individualistic or wasteful, while Martians pride themselves on community and efficiency. Conversely, Earth folks might view some space societies as authoritarian if they maintain strict discipline and hierarchy for safety. These cross perspectives can cause friction or admiration depending on context. In sum, society beyond Earth will be a grand experiment, a chance to reimagine structures under new constraints. It could recapitulate in accelerated form the development of nations and economies with the benefit of hindsight. It will certainly mark the true extension of human civilization beyond our cradle, not just flags and footprints, but laws, markets, and identities taking root elsewhere. When the day comes that a Martian teenager can say, "I want to go into politics," or "I'm starting a business," and they mean on Mars for Mars, that will signal that human society has successfully replicated itself off-world with its own momentum. They will hold elections, run enterprises, and form communities guided by their local needs and values. And perhaps they will send representatives to Earth or a solar assembly to voice Martian interests. That interplay will mark the beginning of our species functioning on a planetary scale, not just Earth, global, but solar, system, global. Will we remain one political unit or fragment? Likely multiple units cooperating, much like Earth itself. The hope is that because space demands unity against a harsh environment, our off-world societies may uphold a stronger sense of human solidarity. As one Apollo astronaut said, "From the moon you see no national boundaries." A Martian might never have seen Earth from space, but they will see themselves from space, on a planet devoid of life except their colony, a tiny human bubble in a huge desert. That perspective might be deeply humbling and foster an ethic of brotherhood with any others out there. So, in forging politics and economics beyond Earth, we may do better than we did under the petty rivalries of old, or we might transplant our old habits, but now separated by millions of kilometers. Likely some of both. The key is that for the first time, human society will become plural societies, and our definition of us will expand. There will be an us on Earth and us on Mars, sometimes at odds, sometimes in alliance, but ultimately part of the grand human story. This evolution will continue as we push further. Imagine centuries hence, societies around other stars, truly becoming interstellar, but one step at a time.
In our near future, seeing a self-governing Mars community or a bustling free trade hub in lunar orbit will be astonishing yet logical. We are, after all, social animals. Wherever we go, we build social worlds. Outer space is just the next canvas for that eternal human endeavor of forming communities bound by shared rules, doing business, and forging identity. Loneliness, silence, distance, exile. In the vacuum between stars, a spacecraft drifts, carrying a few souls encased in metal. Around them, an infinite silence. Or imagine standing on the surface of Pluto, so far from Earth that the sun is just a bright star, and home is an invisible blue dot, an exile in the cosmic dark. These scenarios epitomize loneliness on a scale humanity has never before encountered. The physical distance in space can translate to profound psychological distance from loved ones, from all that is familiar, from the very cradle of life. Even with robust crews and communication links, space travelers grapple with solitude that can seep into the soul. We must confront and find meaning in this loneliness, or it could become our greatest enemy in the void. Nearly every astronaut has spoken of moments of isolation. In orbit, one can always look down and see Earth bustling below, which provides comfort. But as missions extend outward, Earth shrinks in the window until it's just a pale star. That is what we call the Earth out of view phenomenon, feared to cause a deep sense of disconnection. Imagine Mars explorers. At night on Mars, Earth might appear as a tiny pinpoint among millions of other points of light. Will they feel an existential homesickness looking at that distant sparkle, knowing everyone they love is on that speck, unreachable except by delayed radio? Quite possibly. The diaries from crew in simulation experiments like Mars 500 indicated growing emotional distance. Some crew felt like Earth became abstract. Their whole reality shrank to the habitat and 5 crewmates after many months. Actual Mars explorers will have far more stimuli, but also real risk and no easy return. The psychological weight of knowing one is tens of millions of kilometers, and years of travel from home can press on even the strongest minds. We as a species have known physical loneliness. Explorers crossing oceans, wintering in Antarctic night, but space adds cosmic loneliness. It's the silence of the interplanetary void. No sound, no sign of life beyond your crew. Some astronauts report that looking into the deep black of space away from Earth can be chilling, a great black emptiness that makes one feel the smallness of our existence. This humbling awareness can lead to awe or to a kind of anxiety about how fragile and alone we are. Future travelers in interstellar space, with no Earth or Sun in sight, will rely on inner resilience and companionship to not succumb to cosmic ennui. We likely will carry pieces of home, video calls, recorded voices of family, perhaps AI companions that simulate conversations to alleviate monotony. But nothing replaces being with those we love. We must make peace with a degree of loneliness. Space pioneers often mention a sense of purpose that sustains them through isolation. They feel part of something grand, which gives them strength. A Mars colonist might endure because they know they are building a world for future generations. This teleological motivation can fill the void where everyday social fulfillment might lack. In a way, they make friends with loneliness by reframing it as solitude in service of a noble quest. Still, there will be dark nights of the soul. Perhaps a lunar miner after a long shift steps outside the habitat alone and looks at the half-Earth hanging in the black sky. They might be struck by an overwhelming pang. I am not on that Earth with everyone else. I am alone on the moon. An existential isolation no human in history felt until our space age. They might cry inside their helmet, or they might find comfort in the familiar Earth light and whisper, "Hello home, I'll see you soon," to that distant sphere. Psychological strategies form, talking to Earth, keeping journals, and bonding intensely with crewmates to form a surrogate family.
Crew relationships become both salve and potential source of loneliness. In a small group, if you feel misunderstood by or alienated from even one colleague, there's no easy way to find new social contact. You're stuck together. That could amplify feelings of isolation. Being emotionally lonely in close quarters is a peculiar suffering. Mission planners mitigate this by careful crew selection and training conflict management. But inevitably, there could be frictions or cliques. Those not fitting in might feel desperately lonely, even with people around, a phenomenon known even in polar stations or submarines. In space, if someone becomes an odd person out, it's perilous to team cohesion. Thus, missions likely will have counseling protocols. Exile is an ancient human experience. Space explorers might identify with those historical feelings. Reading literature of exile could help them cope and find kinship with Earth-based experiences. Perhaps future spacefarers will draw inspiration from, say, Nelson Mandela's resilience on Robben Island, or the letters of polar explorer Richard Byrd alone in Antarctic winter. They may keep favorite books that tackle solitude to remind them they're part of a lineage of those who faced the void of separation and made meaning of it. Interestingly, while loneliness is a negative state of lacking connection, solitude can be positive, a chosen state for reflection. Many astronauts describe looking out at Earth in quiet contemplation as a treasured solitude. In those moments, they don't feel lonely exactly. They feel connected to all humanity via the sight of Earth, yet separate enough to gain perspective. Future space dwellers might come to cherish certain solitary routines. A Martian might take a solo EVA in a pressurized rover to scout a nearby hill at sunrise, both to do a task and to have a meditative hour alone with the Martian dawn. That solitude can be nourishing, a chance to absorb the wonder of their new world without distraction. Some personalities in a colony might actively seek more alone time, so they volunteer for solo tasks like tending a remote instrument or cleaning an isolated tunnel to snatch those quiet moments. Coping with distance also breeds creativity. People will find novel ways to feel presence across distance. Holographic calls, perhaps. A parent on Mars might tuck in their child on Earth via a hologram reading a bedtime story, albeit with a time delay. Families may keep journals to exchange, something like the same book, traveling back and forth with entries, bridging time and gap. On generational voyages, loneliness and homesickness may evolve into a different sentiment. Their ship becomes the entire world they know, so they aren't longing for Earth they never saw, but they might long for a concept of Earth, a sort of ancestral home in their imagination. That could cause an existential melancholy, akin to how diaspora communities long for an ancestral homeland they themselves haven't seen, but know through stories. They might mythologize Earth as a paradise. Such psychosocial phenomena will shape how much loneliness or belonging they feel. If they strongly identify as "we are the voyagers, Earth is behind us," then not having Earth may not cause loneliness, because their identity is self, contained in their journeying community. They will have created a new home on board or on Mars that fulfills that emotional need. Then the loneliness would only strike when they consider the cosmic isolation of humanity as a whole. But if conversely, Earth remains idealized, they may always carry a void for a home they never knew. In the end, dealing with loneliness in space will be about connection, maintaining human connection across distances, and fostering deep connections within the crew or colony. It will also be about purpose and perspective, seeing oneself as part of something larger. Many astronauts say they never felt closer to humanity than when far above it, seeing all at once. That grand perspective can counter personal loneliness. You feel the companionship of all people implicitly when looking at Earth entire. Similarly, a Martian looking at Earth might remind themselves, everyone I love is there under that glow, and that knowledge, though painful that they are far, is also comforting, because they do exist and are looking back up at the speck of Mars thinking of me. In that mutual gazing, perhaps neither is truly alone. One day, if we find microbes or signals of life elsewhere, that could even alleviate the ultimate cosmic loneliness, knowing life is not isolated to Earth. But until then, each far-flung human outpost carries the weight of being a tiny oasis of life in a vast emptiness. That awareness can isolate, but also unite those in that oasis with a fierce camaraderie. It's us against the void. In that sense, loneliness might be overcome by a strong sense of community and interdependence. The void that separates communities then becomes less frightening because within each bubble there's solidarity, and between them, empathy born of shared adventure. Perhaps future proverbs will reflect this. Far in space, no one is stranger. Meaning if you meet another human out there, you instantly have common ground worth more than any differences. Loneliness might in fact diminish once multiple colonies exist, as they will connect with each other as well as Earth, forming a spacefaring network of friendships. So, while exile is a real concern, human ingenuity, social and emotional ingenuity, will find ways to tame it. We will create new forms of companionship and also deepen our appreciation for the communications we do have. In sum, loneliness in the cosmic ocean is a challenge of the heart that we must and will address with the same vigor as we do vacuum and radiation. By carrying love, memory, and creativity with us, we ensure that even when physically alone, we are psychologically accompanied by our culture and our sense of belonging to humanity. And by forging tight bonds in our new settlements, we build new homes that fill the void of leaving the old home. Thus, even in the silence of interstellar night, the human spirit will not be mute. We will sing to ourselves, tell stories to the dark, and find company in our dreams of those we left behind and those we travel with. Loneliness, then, though ever possible, will not defeat us. It will be met by the fundamental human capacity for connection, reaching outward across any distance, turning exile into pilgrimage. Time and travel, slowness, patience, vastness. On Earth, we measure time by familiar cycles, days, years, the rhythm of seasons, and the pace of a human life. In space, these measures begin to stretch and bend. Journeys between planets take months or years. Interstellar journeys might take generations. The vastness of space imposes slowness on travel that humanity hasn't experienced since the great treks of pre-industrial ages, and even those pale in comparison. To thrive in space, we must embrace a different relationship with time, one of profound patience, long-term thinking, and acceptance of gradual processes. Consider the voyage of a robotic probe to the outer planets. It leaves Earth and spends, say, 7 years coasting to Saturn. For those 7 years, it is in transit, silent, except for periodic check-ins, a testament to how long it takes just to cross our solar system. A human crew to Mars will spend 6 to 9 months in transit each way, essentially committing years including stay for a brief surface mission. Future settlers might endure multi-year transit in a hibernation or confined living. This requires psychological adjustment, to be content during a long journey where days blend and destination is distant. In early seafaring, sailors would spend months at sea. They coped by developing routines, hearty community, and often by slow mental adjustment, where the intermediate time became a world of its own. Similarly, spacefarers must treat the journey not as empty waiting, but as a meaningful phase of life. On a generation ship, the journey is life, entire lifetime spent en route. Time there is measured not in distance to destination, but in the rhythms of their society, births, seasons of the ship's garden, perhaps ship years, defined by some onboard celestial event.
The experience of time dilation is not literal relativistic, but there is a psychological time dilation. Earth and space communities will fall out of sync culturally. Fast developments on Earth might appear in slow motion to a Mars colonist who receives news in big batches due to comm schedules, or vice versa. Earth might be shocked at how quickly a small Mars group changed. Centuries. The vast distances will likely make each colony somewhat like a time capsule of the era it was founded, their culture evolving on its own timeline thereafter. When reconnecting, there could be a fascinating divergence to compare, much as if one could talk to a community that branched off hundreds of years ago. Patience becomes not just a virtue, but a survival skill. Crews on multi-year missions must practice delayed gratification in extreme measure. Scientists on a generation starship might begin experiments whose results only their grandchildren will collect at journey's end. An unprecedented elongation of the scientific process. Colonists terraforming Mars know from the start that they personally will not see a fully terraformed Mars. It might be a project for their descendants, yet they embark anyway, planting trees whose shade they will never sit in. This requires a mindset somewhat lost in our rapid-paced world, a near geological patience and faith in continuity. It harkens to cathedral builders of medieval times, who began construction knowing completion would come centuries later. Humans will need to rediscover that long view to undertake things like terraforming or generation ship voyages. Time in space also behaves oddly on the human psyche. Monotony can make time feel slower. Many Martian analog participants reported that the middle of the mission felt interminable. To counteract that, crews break time into milestones. We made it 100 sols, we're a third through, cause for a special meal, etc., which punctuates and thereby speeds subjective time. On a generation ship, entire calendars might be invented to mark progress, maybe celebrating each light, year traversed, or each percentage of the trip done. These temporal markers serve to give structure and momentum, making vast spans psychologically manageable. Conversely, sublime moments can make time stand still in awe. Many astronauts describe certain minutes gazing at Earth or floating freely as feeling outside of time, deeply present. On long missions, cultivating such moments can refresh spirits, making the slow journey feel worthwhile in the now, not just in the end. Over very long horizons, even the concept of a human lifetime as the ultimate measure might shift. A society that undertakes century projects will inherently place less emphasis on immediate individual outcomes and more on collective, transgenerational goals. Evolution itself might come into play if travel times are so long that humans adapt en route or on new worlds. Thus, time will literally shape us biologically as well as culturally beyond Earth. Ultimately, embracing cosmic timescales could make humanity more resilient and thoughtful. The vastness of space, by forcing patience, may make us wiser caretakers. Projects like sending messages to future colonists or receiving ones from past astronauts create continuity of purpose, a thread of time we hold. Perhaps crews on an interstellar voyage will begin meetings by reading a passage written by the mission's initiators centuries ago, reminding them why they travel, and end meetings by penning a message to those who will land long after they are gone. In doing so, they weave themselves into a tapestry of time that spans far beyond one lifespan, finding meaning in being a vital link in that chain. So while space travel is physically about distance, in human experience, it is equally about time travel of a sort, stretching human presence and plans across far longer durations than we currently operate on. It calls for deep trust between generations. The first must trust the later ones to continue the work, and the later must honor the legacy of the first. If we achieve that, we evolve from a species with short horizons to a cosmic species with eons, wide vision. Imagine a future where it's normal that a project might complete in 150 years.
and people sign up wholeheartedly because they identify with their great-grandchildren as much as themselves. That shift may be essential for our long-term survival. In space, there is no choice. The stars will not be reached by the impatient. In sum, the vast distances impose slow travel, which enforces patience, which in turn may impart wisdom. As one Martian year is nearly 2 Earth years, Martian colonists may naturally have a biannual rhythm and celebrate birthdays only every second Earth year to mark a Martian year of life. They might thus age slower in count. Such playful differences aside, the important part is we will learn to wait without losing heart. Our species will become adept at living in the long now, cultivating crops that take a long time, building ecosystems gradually, journeying far without instant results. And paradoxically, in taking the long way around, we might discover more about ourselves. Freed from Earth's frantic ticking clock, spacefarers might find time for contemplation, art, and fundamental science in ways modern Earth society often doesn't allow. Thus, the enforced slowness might be a gift. It can strip away trivial urgencies and leave focus on the profound. On a starship, one cannot scroll social media or get pizza in 30 minutes. Instead, one might spend an evening discussing philosophy with shipmates or teaching a child the constellations visible from the ship's vantage. Life, though slower, may be richer in certain dimensions. As we adapt to cosmic time, we join the rhythm of the universe. We become comfortable with orbits spanning years, with projects spanning generations, with distances spanning light years. And when one day our descendants sail at near, light speed and relativity causes their time to literally slow relative to Earth, they will know how to handle that too, because by then, humanity will have made peace with time's elasticity. We will carry patience as armor against the tyranny of distance and delay. In embracing the vastness of space and time, we may outgrow some of our short-sightedness. We will plant trees for our great-grandkids on far planets and send ships that arrive beyond our great-grandkids. And by doing so, we ensure that the chain of humanity extends unbroken into that vastness, a slow, steady pulse of life beating against the enormous, otherwise lifeless backdrop of the cosmos. The fragility of Earth, the overview effect, and perspective. High above Earth, astronauts often look down in reverent wonder at the fragile blue arc of atmosphere hugging our planet. From space, it becomes viscerally clear that all of life is sustained by a thin, delicate film of air and a small oasis of water and soil. This realization, known as the overview effect, has been one of the most profound cultural outcomes of spaceflight. It's a sudden understanding that Earth is both immense in beauty and tiny in the cosmos, resilient in life, yet exceedingly fragile in its balance. As we journey outward, this perspective only deepens. The farther we go, the more we appreciate our home world's uniqueness and vulnerability. Many astronauts have returned as ambassadors for Earth's environment and unity. Seeing no national borders from orbit, they report a heightened sense that divisions are artificial and that we are one people riding on the same spaceship Earth. When you go to the moon, you develop an instant global consciousness, said Apollo 14's Edgar Mitchell. That consciousness can reset priorities. Petty conflicts seem less significant than protecting our shared planet. As one orbital observer put it, it's obvious from up here that we need to take good care of Earth. Space explorers notice how thin the atmosphere is, a fragile membrane easily disrupted. They see deforestation scars and shrinking lakes, or pollutants tinging the air. These sights drive home that Earth's biosphere is fragile and currently under strain from human activity. Nothing underscores Earth's fragility more than leaving it and seeing its entirety at once.
a lonely oasis in the black void. Future Mars colonists, living in an extreme environment, might have an even greater appreciation. They will know by daily contrast how abundant and nurturing Earth is. A Martian colonist stepping out of a spacesuit onto a grassy Earth meadow during a visit might be overwhelmed by the ease of breathing and the chorus of life, a stark difference from the barren rust of Mars. Such experiences could breed in them a powerful Earth advocacy. Having lived where life is sparse, they'll fiercely value the fullness of Earth. The fragility of Earth is not only physical, but also emotional for those far away. Earth is the cradle of their memories, culture, and species. To see it as a fragile ball elicits a protective love. This can galvanize support for preserving Earth's climate and ecosystems. Already, space data informs environmental action. But the human emotional element, astronauts speaking poetically of Earth, perhaps moves hearts even more. One can foresee that when colonies exist, they may celebrate Earth Day with particular reverence, honoring the planet that gave them origin and to which most of humanity remains attached. Paradoxically, leaving Earth may be what saves Earth. By seeing its fragility and uniqueness from afar, humanity might unite to safeguard it. Also, as we develop closed, loop systems in space, we get better at sustainable tech that can reduce our footprint on Earth. The life support on a spaceship is essentially an extreme version of recycling and renewable use, lessons we can apply on Earth to use resources more wisely. In that sense, space exploration and environmentalism are allies, not opposites. We learn how precious water and oxygen are when we have to generate and recycle every drop and breath on a spacecraft. Those techniques come home. The overview effect also fosters a kind of humility and awe. Astronauts often speak of how thin and finite Earth's resources seem. It counters the once prevailing notion that Earth can absorb infinite exploitation. From space, it's obvious. A closed sphere with limited land and water, we have what we have. It needs tending, like a garden. This mindset may become common among spacefarers and hopefully filter to the public via their testimonies. One day, if humans live on multiple planets, Earth may be seen as a kind of sacred ancestral home, a fragile birthplace to be preserved, almost like a holy site. Laws might even protect Earth from undue alteration. In science fiction, one sometimes sees Earth turned into a nature preserve with minimal industry, after humans spread out for heavy industry. That scenario is speculation, but the spirit is that Earth's fragility and value become even more apparent once we have other places to do the dirty work. Perhaps heavy mining and energy production will shift to Moon or asteroids, relieving Earth, leaving Earth to be more of a garden and cultural haven, recognized as unique. Standing on another world, a person might look up at the small Earth in the sky and finally, viscerally, understand what all our philosophers have said, that we are one family on a tiny island in space. This understanding, seeded by photos like Apollo 8's Earthrise and Apollo 17's Blue Marble, will only deepen as space travel widens. Perhaps it will lead to more global cooperation. It's notable that the International Space Station, a symbol of unity, emerged partly from that very awareness and has arguably softened geopolitical tensions among partner nations. If a Mars mission is international, those crew will see themselves as Martians together, not separate nationalities. When they look at Earth, they won't see country borders. They'll see one fragile home. And that could reflect back on Earth attitudes via media and education. In summary, leaving Earth has shown us Earth's fragility and need for care in a way nothing else could. It has given us environmental guardians in the form of astronauts and images that have fueled environmental movements. As we go farther, that effect should amplify. Possibly the first human to stand on Mars and look up to search for Earth's pinprick will return an even more passionate advocate for protecting our oasis. The challenge is to ensure this overview perspective permeates human consciousness widely, not just among those who travel. Perhaps virtual reality and ubiquitous space imagery can give ordinary citizens a taste of it.
Or maybe in the future, off-world tourism becomes common enough that a sizable fraction of humans experience the overview effect directly. That could be transformative on civilization scale. A generation of leaders who have seen Earth's fragility with their own eyes might treat global issues with the seriousness and unity they require. Thus, the fragility of Earth lesson might be one of space exploration's greatest gifts to humanity. It holds a mirror up to us from a distance and says, "Take care, this is all you have." It's fitting that traveling so far has taught us to better cherish what is near. In building settlements beyond Earth, we should carry this ethic with us. Treat each new world with respect. Don't repeat mistakes. Mars, for instance, is pristine now. If we colonize it, we should do so sustainably and with regard for preserving its scientific value and any natural beauty. The fragility of Earth lesson can become a general principle. Any world's environment is precious, whether harboring life or not. Finally, seeing Earth as fragile also reminds us of our own fragility. One thin hull breach, one environmental collapse, and life can perish, be it a habitat or a whole planet's biosphere. It's made clear that our survival is not guaranteed unless we act as careful stewards. Yet the flip side is hope. Earth's beauty from space also underscores what an amazing oasis we have. It's fragile, yes, but also tenacious. Life has flourished in that thin film for billions of years. If we make wise choices, it will continue to flourish. The responsibility and the optimism go hand in hand. In conclusion, the perspective gained by leaving Earth might be the key to saving Earth. The more people internalize the view of our planet as one delicate ecosystem in space, the more likely we are to behave in ways that protect it. Thus, as we voyage outward to find new worlds, we may, somewhat paradoxically, ensure the old world remains healthy. In caring for our fragile Earth, we demonstrate that we have truly learned one of space travel's fundamental lessons, that there is no place like home, and home must be guarded with all our skill and heart. How? Ethics. Should we go? Amid the excitement of starry frontiers lies a fundamental question. Should we venture out at all? Just because we can reach other planets or build powerful technologies, do we have the right or the wisdom to do so? The ethics of space exploration and colonization demand careful thought. We must balance our drive to discover and expand with humility, caution, and moral responsibility to other life, to our own humanity's needs, and to the cosmic environment. One ethical concern is the risk of neglecting Earth. Critics ask, why spend billions to send humans to Mars when people on Earth lack food, or when climate change threatens our existence here? Isn't it unethical to divert resources outward while home needs fixing? This is a compelling argument. The counter argument is that space exploration yields knowledge and innovations that help Earth, and that it addresses fundamental human curiosity that enriches our civilization. Still, the critique has merit. We must ensure our push outward does not become an escape from problems we should solve here. Many space advocates argue it's not either or, we can do both, and indeed, the overview effect has helped Earth's cause. Ethically, it may be seen as acceptable to explore if we keep Earth's well being as a priority as well. The ethic might be, do no harm to Earth in the process of leaving it, and ideally, help Earth through what you gain. Another ethical dimension: planetary protection. If Mars harbors even microbial life, our arrival could contaminate or even destroy that biosphere. Is it ethical to colonize a world that is already an ecosystem for native life, however simple? Many argue it would be morally wrong to wipe out Martian life for the sake of human expansion. This parallels historical colonization mistakes, but on an interspecies, interplanetary scale. Accordingly, current policies require us to search diligently for life before establishing crewed bases. If Mars is found sterile, then the ethical issue shifts. Perhaps then we have a green light to terraform or populate it. But if life is found, humanity faces a profound choice. Leave Mars alone as a sanctuary for that life. Attempt a controlled cohabitation where we restrict human areas and leave wild Martian life zones untouched. These decisions will be ethical crossroads. Some ethicists say we have a duty to allow alien life its own evolutionary path without interference, a kind of cosmic bioethics principle. Others suggest if Martian life is microbial and limited, humans could ethically introduce Earth life to start a richer biosphere. This ties into whether we view ourselves as gardeners of the universe or guardians of pristine nature. There's no easy answer until we know what's out there. What about ethical use of space resources? Space offers immense materials, which could help human prosperity. But who owns them? And is it fair for wealthy nations or companies to stake claim and profit? The Outer Space Treaty says no nation can claim sovereignty, but newer laws allow companies to mine and own extracted resources. Some argue this is ethical if it benefits humanity broadly. Others fear a space gold rush that leads to inequality or conflict in space. Possibly an international regime needs to oversee space mining ethically, perhaps requiring those who exploit space resources to share a portion of benefits globally. The ethics of economic expansion in space revolve around justice and equity, ensuring space is not just for the rich, and that its wealth, if tapped, helps reduce poverty or hardship on Earth, not just line corporate pockets. Human rights in space also come up. If settlers are under a corporation's authority, we must ensure their rights and well-being. Historical colonialism had abuses, debt bondage, exploitation. We must avoid repeating that off-world. This means establishing legal frameworks so that space colonists have representation, safety standards, the right to leave and return to Earth if they wish, etc. A Mars colony ethically should not become a penal colony or forced labor camp under guise of exploration. It should be built on consent and enthusiasm of its members, and they should maintain the right to dissent or shape their governance. Environmental ethics extend beyond Earth now. We have to consider whether it's right to reshape entire worlds or litter orbit with debris. Our activities can damage space environments, e.g. Kessler syndrome from too much orbital junk could make launching dangerous for decades. Ethically, those who put objects in orbit have a responsibility to de-orbit them at end of life or find solutions to clear debris. For other planets, even if lifeless, there's value in preserving their natural state for scientific and aesthetic reasons. Possibly a compromise ethic, terraform partly or in contained ways, preserving some regions, or time, phase it. Do pure science study for, say, another 50 years, then consider larger projects. Another angle, should we risk humans at all? It is dangerous, people will die. Is it ethical to send astronauts on a one-way mission to Mars, where they might perish of radiation or accident? Those individuals can volunteer, yes, but society sanctioning essentially a likely fatal endeavor is heavy. Historically, explorers risked death and society accepted it for greater good of discovery. If the individuals are fully informed and willing, many argue it is ethical. Human spirit compels exploration even at personal risk. But we must not be cavalier. We owe them best possible safety measures and an open acknowledgement of risks. The ethics of crew care mean we must also consider mental health risk. Only if they are screened and willing. Some suggest use robots and AI instead of humans for initial exploration due to risk, an ethical calculus valuing human life highly. Yet others respond that the human presence is invaluable in ways robots cannot replicate, and that consenting adult explorers have the right to risk themselves for such meaningful endeavors. Intergenerational ethics arises in projects like generation ships or terraforming. Those choices commit future unborn generations. Is it ethical to send a generation ship knowing future children will be born in space, with no choice in being there, possibly unable to ever go to Earth? We touched on that in children's section. It's a weighty moral thing to consign descendants to a particular path. One might argue it's only ethical if that path clearly leads to a viable world for them. If the mission is too uncertain, it edges into risking the fate of future people without their consent. Imagine if halfway the ship fails and the later generation has no way back. Some could say the original planners did something unethical. To mitigate that, planners might build in abort options or make the ship itself as comfortable and complete a world as possible, so that even if they never land, successive generations can live decent lives on the ship. Terraforming binds future generations to upkeep a planetary project they didn't start. Is that ethical? If it's beneficial, perhaps yes, as it expands their opportunities. But if it requires centuries of labor with no guarantee, some might consider that presumptuous. This echoes classic ethics of long-term engineering. Is it right to start something huge that one's descendants must finish? Many say yes, if it's for their eventual benefit. No, if it burdens them without clear payoff. In weighing, should we go, one might also consider philosophical arguments. Some philosophers question if expanding into space addresses or distracts from our spiritual and ethical development. Does moving outward help humanity become wiser or just spread our follies? One ethicist might say, first achieve harmony on Earth, then expand, otherwise we risk exporting conflict and inequality to other planets. Another might argue that expansion is part of humanity's growth and will, in fact, drive us toward greater unity and wisdom through perspective gains and new challenges. Animal rights might also enter the picture. If we take animals to space, what are their welfare standards in such artificial habitats? Perhaps future colonies ethically decide to be vegetarian until they can provide humane conditions for livestock. Already, we try not to send vertebrates to space unless necessary for science, mostly small invertebrates now. In a colony context, eventually people may want pets or livestock. Ensuring those animals aren't unduly stressed by low gravity or enclosed spaces will be an ethical concern. Finally, the ethics of planetary defense and backup. Some like Elon Musk say it's our duty to become multi-planetary to ensure human survival. One could frame that as an ethical argument. Safeguarding the species is a moral good. Others might argue focusing resources to prevent those catastrophes on Earth is more urgent ethically than establishing a Mars colony as insurance. Both approaches aren't mutually exclusive, but resource allocation is always an ethical debate. In conclusion, should we go is answered by many with yes, but responsibly. The ethics urge that we do it carefully, protect Earth, do not harm other worlds or life, ensure fairness and safety for participants, and share benefits widely. That means strong international cooperation and law must guide our steps, making space the province of all mankind, as the treaties declare, not a wild west of exploitation. If we adhere to these ethical principles, space exploration can be a noble endeavor that elevates humanity, rather than a reckless indulgence or new colonialism. The very debate is healthy. It forces space agencies and companies to consider impacts deeply before acting. As a result, our ventures are more likely to be sustainable and just. By grappling with, should we go, we refine how we go, making sure that as we expand our physical presence, we also expand our moral circle. The dream of the stars, then, isn't just a triumph of engineering, but also a triumph of ethical progress, showcasing that humanity can extend its reach without losing its conscience. Indeed, perhaps confronting the cosmic environment, so empty and free of moral agents except us, compels us to become the moral agents of the cosmos, carrying ethical consideration to places where previously there was only barren matter. Thus, yes, we should go, but guided by humility, respect, and wisdom. In doing so, we answer the question not with mere ambition, but with a thoughtful and principled approach that honors life, both ours and whatever we encounter, and honors our home even as we leave it. If we cannot do it ethically, perhaps we shouldn't go. But I believe we can rise to that challenge. In fact, the very process of debating it
is a sign that humanity is striving to grow ethically in tandem with its technological growth. And that gives hope that we will be careful shepherds of the wider solar ecosystem, not just explorers. Hope, evolution, expansion, and endurance. Through all these trials, the distances, the dangers, the solitude, the labor, one force propels humanity outward: hope. Hope that we can evolve beyond our infancy, that we can expand the realm of life, and that by spreading out, we ensure our long-term survival and growth. In the vacuum of space, hope is as essential as oxygen. It is the quiet confidence that our efforts will lead to a better future for our species. It's the belief that even if Earth faces perils, humanity will endure among the stars. Space exploration often lights a fire of inspiration in the young and old alike. It suggests that no challenge, not even the infinite void, is insurmountable if we apply creativity and solidarity. This fosters a hopeful mindset. We solve enormous problems step by step. Each success, a safe landing on Mars, a year lived off, world, builds hope that bigger dreams are within reach. We begin to feel that as daunting as climate change or resource limits on Earth are, a species that can colonize lifeless planets can also fix issues on its own verdant one. The ingenuity and perseverance required for space breed an optimism of capability. We can do hard things. Evolution here is not just biological, but also cultural and intellectual. Living in space will force us to evolve new social norms and technologies which can loop back to improve life on Earth. For example, needing to recycle everything in a closed habitat pushes advances in recycling tech that we can use Earth-side, fueling hope that we can become sustainable globally. If humans adapt genetically over generations in low gravity, that's an evolution of our species itself, a hopeful sign that we are not static. We can continue to change and survive in varied conditions. Our very DNA may eventually carry the story of our travels in subtle ways. Expansion of humanity into multiple worlds carries the hope of diversity and resilience. A multi-planet civilization is far less likely to be wiped out by a single catastrophe. This is often cited by visionaries. Being single, planet is precarious. Multi, planet gives a backup and fosters innovation from diverse environments. It's like a species spreading to multiple islands, more chances to survive storms or changes. Knowing we have people on Mars and maybe habitats in orbit might relieve that subconscious anxiety that all our eggs are in one basket. It gives hope that even if Earth suffered a tragedy, humanity would continue elsewhere, perhaps even able to help restore Earth eventually. So expansion is a kind of insurance, but also a positive assertion that life wants to spread. There is something inherently hopeful about planting a garden in new soil. It is an act of faith in the future. Endurance ties in. The thought that by moving into space, the human story will endure far, far into the future. Carl Sagan noted that if we stay only on Earth, sooner or later we face extinction. But a spacefaring civilization can potentially last for millions of years and across many worlds. That concept, that we ensure the continuity of our lineage, is deeply hopeful. It says that all our art, knowledge, and values need not vanish. They can be carried to new frontiers and seed new branches of civilization. It transforms our cosmic perspective from one of possible doom to one of open-ended journey. The knowledge that we have backup homes could instill less existential dread in society overall. Space also engenders hope by uniting people under shared goals. The Apollo-Soyuz handshake in orbit in 1975 during the Cold War, the cooperative ISS during turbulent earthly politics, these give hope that common endeavor can bridge conflict. A future where American, Chinese, Russian, Indian, and European astronauts build a Mars base together is one where people might think, if we can do that together, maybe we can solve conflicts on Earth too. The triumph of cooperation is a hopeful model. The sheer beauty and wonder encountered in space
Earthrise views, rings of Saturn, newborn stars in nebulae, fills one with hope in the grandeur of the universe. It suggests a positive notion that there is so much more to experience and understand. We are not confined to a doomed rock. The cosmos is full of possibility and perhaps other life or new knowledge that can enrich us. This can combat despair by replacing it with curiosity and a frontier spirit. Certainly, there are cautionary voices, and rightly so. We must be careful. But caution doesn't kill hope. It just guides it. We temper rash optimism with wise planning, but we still hope to succeed, and thus plan meticulously because we hope. In an imagined future, perhaps centuries hence, humans might gather on multiple worlds on a particular day, say a Human Heritage Day, to jointly commemorate when humans first left Earth. They might transmit speeches or messages to each other at light speed lag, reflecting how far we've come. They might speak of the perseverance of their forebears through dark times and celebrate the flourishing present. Such an interplanetary festival of unity and endurance would itself be the fruition of the hope that drives us today. We can envision those distant children of Earth, living confidently across the solar system and maybe beyond, looking up at the stars we once inhabited and saying, they had hope, and we are the living proof that it was not in vain. Every step of this journey, from the first orbit to the first step on an exoplanet, is built on hope that the step will lead to another. In sending Voyager probes beyond the solar system, we even attached golden records with sounds and images of Earth, a hopeful greeting to any who might find them, and a time capsule for future humans too. It was an act of optimism that knowledge and goodwill should be cast into the cosmic sea, trusting someone or something will receive it. In the end, the question, should we go, can be answered in part by, we should go if it feeds the better angels of our nature. And it does. It gives us perspective, unity, innovation, and aspirational goals. These are hopeful qualities that can help solve problems at home too. Thus, our expansion is not an escape from Earth's problems, but a catalyst to solve them, and a promise that even if some problems cannot be fully solved, humanity will still have a future. It's a plan B that reinforces plan A, because those who venture out gain perspective that makes them more determined to protect Earth. It's as if by ensuring our species' endurance, we free ourselves to tackle today's challenges without fear-driven paralysis. There is also a broader hope that in carrying life to barren worlds, we infuse the universe with meaning and diversity. Many see a moral good in spreading life's light, a form of cosmic altruism. If we someday green Mars, we will have taken a sterile planet and given it ecosystems. In doing so, we continue the work nature began on Earth. That continuity is hopeful on an almost spiritual level. Life becomes harder to extinguish and more abundant. Even the potential contact with other intelligences is a hopeful intrigue. By exploring and sending messages, we express hope that we are not alone, or that we can at least announce our presence to the universe. It's a gesture of optimism to include a greeting on every interstellar probe. It shows we expect there could be someone to greet. And if one day we do find evidence of others, that will open a profound new chapter, fraught with caution, yes, but also fulfilling one of humanity's deepest hopes, that life and mind aren't unique to us, that we can learn from peers among the stars. Ultimately, the journey into space is an expression of one of humanity's best qualities: hope in progress and discovery. We have always looked up and wondered. Now we leap up and wander. That act, born of hope, will likely ensure our long-term survival and growth. It is fitting that many rockets are named with hopeful words. As our habitats expand, so will our hope, each success reinforcing that initial faith in ourselves.
Standing on the threshold of the cosmos, we choose hope over fear. We choose to venture forth believing the risks are worth it, that the unknown holds wonder, not just danger. And time and again, our experiences, from orbiting Earth to walking on the moon, have validated that hope with tremendous rewards of knowledge and perspective. So in hope, we go. Carefully, yes, and ethically, yes, but boldly as well. Hope is the sun lighting our way in the dark ocean of space. As we sail farther, that sun of hope rises ever higher, illuminating paths we once thought impossible. In the grand cosmic morning, we find ourselves not lost in infinite night, but at the dawn of an open future, our horizons unbound. In that lies the ultimate hope, that humanity's story is just beginning, and that by venturing upward and outward with wisdom and compassion, we set the stage for countless chapters to come among the stars. A final meditation, home now among the stars. Picture a lone explorer standing inside a transparent dome on a distant world. Through the glass, they gaze not at Earth in the sky. Earth is far behind, but at a starfield of unknown constellations. Perhaps nearby, a new sun rises over alien hills, casting blue shadows on the ground. Behind the explorer, a settlement's lights twinkle, a cluster of habitats and gardens under domes. In the sky, there might be the faint glow of an orbiting ship or station, the vessel that brought them, or a satellite linking them to far-off humanity. The explorer places a hand on the glass and feels a swell of emotion. This is not Earth, yet it is home now. In that quiet moment, they reflect on how far humanity has come. The stars once fixed in legend are now locales visited or lived at. They think of the person in orbit overhead, perhaps a loved one on a ship bound further outward. Once, that would have felt like unbearable separation, but now it's part of the tapestry of their lives. Distance has become relative. Love and connection persist across light, years through the beams of comm lasers carrying heartfelt messages. They feel no less connected to that person than an earthbound person feels to someone across an ocean. Human bonds have stretched across space and remain strong. The explorer's mind drifts to Earth. On a clear night occasionally, their settlement can spot Sol, our original sun, as a particularly bright star among others. Earth itself is too small to see without a telescope now, but the explorer knows it's there, circling that star along with Mars, Jupiter, and all. What a marvel, they think, that we came from that tiny spark and built new lives out here. They don't feel sadness now, because they carry Earth within them, in their accent, in their customs, in perhaps a locket of pressed flowers their grandmother gave them from an Earth garden long ago. Earth lives in their heart, and they realize something profound. Home is not a single planet or place. Home is the community of life and memory they carry. They smile, looking at the new world's landscapes. Once, their ancestors felt exiled leaving Earth, but over generations, that ache transformed into a sense of belonging on this world too. They have made it familiar, seeded earth plants in its soil, built houses filled with laughter and art. The distant starry skies no longer intimidate. They inspire. Where once an earthling looked up and felt lonely, now this explorer looks up and feels accompanied, knowing humanity is out there on other planets, on ships between the stars, forging new connections. They think of the old term, the void of space, and gently shake their head. The void is not empty anymore. It's dotted with human outposts, with our probes and signals, with the light of our curiosity. The universe has become, in some small measure, alive with us, and in turn, we have become larger, not in ego, but in understanding.
We see ourselves as part of a cosmic family of worlds now. This person in the dome might have friends on 3 different planets and correspond with colleagues on a space station orbiting a distant moon. Their concept of neighborhood has expanded unimaginably from centuries ago, yet to them it feels normal. They place a palm on the cool glass and feel grateful to those early explorers who took the first steps to allow this moment. That first person in orbit who gasped at Earth's fragility, that first moonwalker who spoke of a giant leap, the first Mars crew who braved isolation. All those courageous souls carried the flame of humanity outward. Now it burns securely here on this far planet, warming homes, fostering life and culture anew. The explorer murmurs a thank you, perhaps even saying a small prayer or good wish that those pioneers know their legacy thrives. Outside, an alien wind blows dust across the plain, a reminder that this is not Earth. Challenges remain. The air outside is unbreathable, and the dome is life's shield. But the explorer doesn't feel fear. They feel pride in how well their society has managed, how they've bent this harsh environment gradually towards habitability without losing reverence for its original state. Nearby, a patch of transformed soil shows green sprouts, part of a centuries-long terraforming experiment carefully monitored. It's small now, but it symbolizes hope that one day, this world too will host forests and lakes under a human-made sky. Whether that happens in their lifetime, they don't know, but they find comfort that their children or grandchildren might walk freely on this land. The distant ship in orbit is preparing to depart further outward, perhaps a generation ship destined for another star. The explorer in the dome thinks of the people aboard that ship. Some dear friends are among them. It could be 100 years before that ship sends word of arrival. Yet the explorer smiles, because this is how far humanity's trust in the future has come. We plant seeds we will never see fruit, with faith that others will harvest. That ship is an ark of our species' hope, leaving from this colony, which itself was once the frontier. In the dome, the explorer hums a tune, an old Earth lullaby they will sing to their child tonight. Overhead, as twilight falls, a familiar pinpoint appears. It is Earth's sun setting, small, but still golden. The explorer whispers softly a line from that lullaby. Though worlds divide us, our hearts are one. In that simple phrase lies the truth they live by. That distance cannot truly divide the human family. We have found ways to remain one people across many homes. As the stars ignite in the darkening sky, the person feels a profound peace. They turn and look at their settlement. Through another window, they see their child waving at them from inside, calling them in for supper. They wave back and begin to head home. Home, a word that now has many layers for them. Home is the cozy lit room where their family eats and laughs. Home is also Earth, shining afar, cradle of their lineage. Home is the new planet under their feet, adopted fully. Home is even the spaceship departing, carrying friends and hopes, an extension of their community. And home, ultimately, is the universe itself, now not a void, but a network of places where humanity resides. They step through the airlock into their habitation, greeted by the scent of stew. Their child runs up excitedly, asking, "Did you see the starship go?" They kneel and hug the child, answering, "Yes, I watched it sail. One day, you might sail to another world too." The child smiles, unafraid. For this little one, the idea of multi-year journeys or multi-planet life is normal. They were born into a multi-planet humanity. They will take it forward. In that warm embrace under an alien roof, in that moment of familial love carrying on light years from Earth, we see the fulfillment of our ancestors' greatest hopes. We endured, we ventured,
We found and made new homes. We brought life where there was none, and learned anew how precious life is. We linked star to star with our courage and caring. Looking over the child's shoulder, the parent sees through the window the glimmer of the departing starship one last time before it vanishes into the night. They silently wish its crew well, safe journey until our paths cross again. Perhaps decades from now, their descendant will receive that ship's hail from another sun. That thought is astonishing yet plausible now. The parent feels tears, not of sadness, but of awe and gratitude. In the great tapestry of the cosmos, humanity is weaving bright new threads. We are no longer confined to one small patch. We roam and create across the vast black cloth, connecting distant points with lines of travel and communication, turning the darkness into a canvas of our journey. They think of the word home. It used to mean the valley or country one was born in. Then it expanded to mean Earth when we saw Earth from space. Now, for this person, home is both Earth and this new planet, and potentially the stars beyond. Home has become wherever humans live in harmony. With a final glance through the window at the stars, which no longer seem cold, but inviting, the explorer closes the shutter. Inside, their family gathers around the table. They join them. A window is open to a greenhouse pod, where a night, blooming flower brought from Earth spreads its fragrance. On the shelf is a small globe of Earth, and beside it, a small model of this planet. The family keeps both as cherished symbols. They begin to eat and share stories of the day. Laughter fills the habitat. Outside, the alien wind continues to blow, but the human colony shines with warmth and life against the alien night. In this simple scene lies something extraordinary. Humanity has made the universe our home. We carry our flame of life wherever we go, and it brightens the lonely darkness. What began with someone peering out of a tiny capsule window at a blue Earth has led to people living and loving under distant suns. The question, what if we could live in space, has been answered by their very lives. No, they are no longer visitors. They live here, and they do not feel lost or adrift. They have found connection, even far from Earth. Their children will call this world home without a second thought, and will learn of Earth as an origin they respect and perhaps visit, but maybe do not yearn for with pain because their life is full here. This is home now, not in the sense of replacing Earth, but adding to Earth. Humanity has not forgotten its birthplace. In fact, we appreciate it more, but we have also embraced new homes, proving the spirit of home can be created wherever we bring our humanity. As the family in our final scene finishes dinner, the child sleepily asks for a bedtime story. The parent chooses perhaps the story of how humans first left Earth, a grand tale now part of their lore. The child listens, eyes shining, to the adventures of Armstrong, of Curiosity rover, of the first Mars landing, of the great journey that brought their grandparents to this planet. In the child's mind, these aren't just bedtime myths. They are the stepping stones that allow them to exist and dream. After the child is tucked in, the parent steps outside the habitat one more time. They look up at the night sky, toward the invisible little star that is the sun, and say softly, "We did it." Perhaps they are speaking to the pioneers of old, or to Earth itself. "We carried your light this far, and we will carry it further. You are with us in every step. Rest well. We are home among the stars now, and we will not forget you." With that, they go inside to join their family in sleep. Outside, the camera of imagination pans upward, from the glowing human settlement out into the sky, showing the planet from afar, a tiny spark of life on a foreign orb. And beyond, stars upon stars, no longer out of reach, but destinations awaiting us. Our view fades with the knowledge that humanity has begun a new chapter, one not of exile, but of expansion grounded in remembrance of Earth's fragility and a commitment to carry Earth's legacy responsibly outward. In myriad habitats scattered in the cosmic night, human hearts beat with love and hope, connected by threads of light and memory across the emptiness. We end on the image of Earth itself as seen from that distant world, a pale blue dot in a sunbeam, as Carl Sagan described. It hangs like a jewel in the vastness, but it is not lonely, for around it in the darkness now glimmer other lights of human presence, faint but growing. The family of Earth has begun to leave lights on elsewhere in the universe, assuring that the light of consciousness and life will not easily be snuffed out. That image encapsulates the spirit of all our striving beyond Earth. We venture forth not to abandon our home, but to spread its light, to ensure that what is fragile becomes enduring, that what is unique becomes ubiquitous in the cosmos. We go to know ourselves better, to protect what we love, and to seek companionship in the endless night. In that final view, Earth shining, joined by the tiny new lights of our off-world homes, we find an answer to, what if we could live in space? The answer is, we can, and in doing so, we come to realize that space was never truly empty. It was waiting for us to bring meaning to it. By living in space, we do not lose Earth. We carry Earth with us, and in turn, gain the universe. And so under alien skies, humanity finds itself again, hopeful, connected, and at home.